this kind of thing. They write documents, they produce documents that describe things. Not just networking, they do all kinds of standards for many different kinds of things. Open systems and connections. So the thing to consider on here is the number 7, a 7-layer model. In contrast, there's also the Internet 4-layer model described in this RFC. So if you go look at these RFCs and look up RFC 1122, you'll find the description. So this is a kind of a curiosity, because the RFCs are standard, and the standard is trying to define a layering model that the standard should follow. So it's sort of combating and kind of recursion going on there, but don't worry too much about that. So what we've got here are two popular recommendations on how to structure a standard. They're not saying what how the internet works at all. They're recommendations on how you might write a document that describes how the internet might work. We're still quite far away from actual code here. But of these two, the important one really is the 7-layer model. It's the one that was thought out properly, or at least reasonably properly. Used widely to read books and papers about networking protocols and networking standards. On the other hand, the Internet 4-layer model is essentially a model that was slapped together when people thought models were a good idea. How many layers do we have in the model? Well, we've got the internet out there, it has 4, so let's do 4. Nothing more sophisticated than that. So on the 7-layer model is where you start with the model and then you should go away and do the standards to follow it. The Internet 4-layer model was, we've got the implementations, let's be proper computer scientists and have a specification for the thing that we've already written. A lot of your life will be going back and fixing the specifications to match your code. It's the way it's done. Anyway, so the OSI model is the one that's sort of properly done and the one that we really ought to be thinking about. But talk about the 4-layer model because it is more close to the way real life actually happens. As in, it's a big fudge to make things work. Anyway, these layers, they're pretty much got to be bite-sized chunks to help you write your document, your standards document. So they've got to be easy to implement, represent a well-understood concept. You don't want anything too complicated in these things. Each layer should only ever reference its 2 neighbouring layers. A layer at the bottom shouldn't need to know what a layer at the top does. So everything's sort of as local as it possibly could be. Chosen so the meta-information flowing across the boundaries is minimised. This is a fancy way of saying that each layer should understand or know as little as possible, as little as you can get away with about its neighbouring layers. They'll need to know something because they have to interface with these neighbouring layers, but try and keep that to a minimum. The more connection you have between layers, the more things are tied together, the harder it is to change things. A layer must be as self-contained as possible and knows little about all the layers. The idea that you might be familiar with writing code, modularity, a module of is a chunk of code which does a certain thing. You know how to interface with it, but you shouldn't have to know what's actually going on inside it to use it. So here we've got the same kind of idea, but relating to a document, a standard. And again, for exactly the same reasons, is to make things manageable and make things more flexible. So an implementation of a layer can be removed and replaced by a different implementation without affecting the overall system. Seems fair enough. We understand that with code, but now we're talking about implementations of standards. You would be very upset that every time you move from using Wi-Fi to using Ethernet to using a cellular phone, if you had to use a different browser for each one, simply because the physical thing going on underneath had changed. Why does your application have to change? Why? Well, here we have this layering is going to give us this behaviour. It's not just by magic it's because these things are specifically designed in this way, such that applications do not have to know what's going on down below in the system, in the hardware. Indeed, the other layers in our system don't have to change as well. You don't have to change from using the language of the web, HTML, hypertext markup language, simply because you change something else in the system. You don't have to rewrite or replace the code that does that, or run it over a different network protocol because something else changed. All of these different layers, they can be as ignorant as possible of anything else that changed. Modularity helps us do these kinds of things. Any one of these things you could conceivably change without the other layers knowing. Okay, so I need to describe the 7-layer model, the ISO, the Standard Organization 7-layer model, because it's the one you always talk about when you talk about networking standards. 1983, it makes it really, really ancient. Should I ask when you were born? Possibly not. Were you born this century or last century? Some. Okay. So, well, this is prehistory, yeah. Didn't even have computers. We all did it on abacuses and stuff. 1983. So it's been around a long time. Which is to say, because it survived this long, that tells us it's actually quite important. 7 layers. There you go. Physical data link network, transport, session, presentation, application. Now, at some point in your life, you'll be waking up sweating in the middle of the night, reciting those 7 layers. So we're going to go through each of these layers and just give you a brief indication of what these layers are about. Physical, you can kind of imagine. Application, you can kind of imagine. Just all this kind of weird stuff in the middle will be the bits that maybe you've not seen before. Each layer does one thing, right? Ideally, each layer does one thing, one well-defined concept. And each layer will know as little as it possibly can about its neighbouring layers. So, starting off with physical layer. Physical layer, sometimes called the phi layer. If you go and talk to electrical engineers, they do their bit in networking by actually physically building their stuff. They're very much more about the phi layer and things like that. Sometimes called layer 1 as well. Hardware. It's deals with transmission or bits over a channel. So it's sort of the physical thing that you need to get data from one place to another. And in this layer, you might like to consider all kinds of physical things, physical attributes. What voltages to use? I mentioned this previously that when you plug one thing into another thing, they've got to be compatible on voltages, otherwise something explodes. What colours are light pulses, radio wavelengths to use, all of these kinds of physical attributes. These have to be decided somewhere, and what we're saying is it's a good idea to decide them here, in this chapter of your standard, if you like. What encoding for bits? So bits, 0s and 1s, need to be encoded in the physical medium somehow. And you might think, okay, 0 is a 0 volts and a 1 is a 1 volt or something like that. But it turns out there are lots of problems with that. And so you'll have more sophisticated stuff. What colours of light do you use to encode your bits? How do you encode bits in terms of photons? Also, how long should a bit be? Should it be a millisecond long? Should it be a microsecond long? In terms of an electrical signal? What these kinds of issues? You need to decide, so do that here. Then you've got that other kind of things that once you realise you've got to do it, you think, oh yeah, I suppose I ought to do it, but how many wires do you use in a cable? The sort of things that you need to think about if you've got a cable. We've got any cables lying around? Cables with plug pins in the end, that's got to fit into the socket. Plugs and sockets have got to match. seems blindingly obvious, but someone's got to write down what the standard is. Here is a good place to do it. What plugs to use, what sockets to use. And there's been various changes over the years to plugs and sockets. In the very early days of the internet, plugs were really big and heavy things, forever falling out the back of computers. Network plugs. These days they're very small and sort of a chunk and a clip when you put them in. But they've changed over the years. And much more. Too much more to talk about right here, but there's a lot of aspects of the physical nature of your system you have to think about. The OSI model says, think about any aspects with choices regarding hardware. Make sure that when you plug two things together, first of all you plug in the socket, they're compatible, and the signals going down the wire or the optical fibre or across the wireless airways, they're all compatible and all these kinds of things. Next layer, data link layer. Some of them called layer 2, some of them called the MAC layer, the media access layer. Again, media access is more of an electrical engineer kind of phrase, but it's the element of the interface that gives you access to the medium, that is the physical thing. TICS, the physical layer, tries to create a channel where there are no undetected errors of transmission. That's a fairly fuzzy statement, but it's called the link layer, because this is your link, your connection between this machine and the next machine on the local network. It's just a link. And the link might be with a wire, it might be a radio link, but it's sort of a one talking to a one thing. You want to create a channel with no undetected errors. At least this is what the recommendation says. Undetected errors. Well, first of all, we're thinking about errors. We have to think about errors because we know the physical world is not 100% reliable. At some point, we're going to have to take errors into account in our system. If I want data to move from my machine to your machine and have it correctly transmitted, there's got to be some mechanism for detecting when something went wrong. The transmission wasn't flawless. Wireless networks are indeed fairly unreliable. There's lots of stuff. Your Wi-Fi network seems to work well, but that's only because it knows that there are lots of errors going on all the time and managing to fix them by various mechanisms. Wi-Fi is quite a highly errored, if that's a good phrase. A medium that has quite a high error rate in it. Going along copper wire on an Ethernet cable, there are going to be a few errors, but very much lower percentage of errors. But whatever, there are errors sometime. And so they've got to be dealt with somewhere, and the 7-layer model recommends deal with those kind of errors here. Of course, if an error is undetected, you can't do anything about it. So part of what we need to do here is making sure we can detect errors when they happen. In a typical implementation following this, you might find a MAC layer sending a sequence of what they call frames, that is, bunches of bits. A frame is just some number of bits or bytes, maybe tens or maybe thousands of bytes long, but one chunk, and then another chunk, and another chunk, and another chunk. A sequence of frames. Frame is just another word for packet. But hello.
Sorry, I didn't quite hear. Does this layer re-request packets?
Well, it doesn't make any specific recommendation. It says, why don't you think about errors here? It doesn't say how you should fix it.
Right.
But it says you should think about how you would fix it. Okay. If you understand the distinction. It's saying you should think about it here, but not giving it any concrete recommendations. Because different people might want to do it in different ways. Different standards might want to use different approaches. in fact, it turns out that some MAC layers do a retransmission. There's some mechanism to spot something when it goes wrong, and one end retransmits one of these frames. Again, using frames here such that we can have sort of a retransmission. This packet got lost, this frame got lost, please retransmit this frame, rather than something went wrong somewhere in a continuous stream of bits. So some, in real life, some implementations of standards following this do a resend. Some don't do resends, but have a more complicated encoding of the bits inside the frames. So it's not just the bits, it's bits plus extra information, error correcting codes, if that means anything to you, that allow the other end to spot there's an error and sometimes even correct errors inside the bits it's just received. So two very different ways of dealing with errors. Some do this, some standards do this, some implementations of standards do this. Turns out another popular choice at this point is do nothing at all. Let somebody else figure out that was an error. Somebody else, i.e. some other layer, figure out there was an error. So this sounds a bit weird in that we've got this recommendation that you deal with errors here, but some standards don't deal with errors here. Well, this is just life. Layering model is a suggestion on what you should do at each particular point. It's up to you to follow in your standard the suggestion or not. Some do, some don't. Some say they've got a better idea on how to deal with errors. So already I'm saying that just because we've got this nice, neat 7-layer thing, doesn't mean to say reality is like the nice, neat 7-layer thing. Reality quite often diverges quite a lot from the nice, neat theory. Theory and practice can be very different. Okay, real life can vary. Whether it's right or wrong to do that, that's an entirely different question. Sometimes it is and sometimes it isn't. Anyway, so the link layer deals with the connection to the local network. That is, this machine physically connected by a wire or an optical fibre or something to another bunch of machine or machines. That's sort of local stuff. So we've also got to deal with non-local stuff. This machine here talking to a machine on the other side of the world. Yeah, the machine, we're talking about the machine on the other side of the world. It's on a completely different network. It might not be on an Ethernet. It might be on a completely physical kind of network. So your link is an Ethernet connecting, an Ethernet wire connecting to Ethernet cards. The next layer to deal with when you're talking to a completely different machine, maybe on a completely different hardware. This is what the network layer does. Layer 3 controls the operation of the wider network, particularly the issue of routing. The network layer 3 is really mostly about routing. That is, how do packets know how to get to their destination? Well, I already said the packets don't know, but how do packets get routed to their destination? Routing is the question here. Again, the 7-layer model doesn't give any particular suggestion on how you solve this problem. Out there in the real world, there are lots of interesting solutions, but the 7-layer model says, think about it at this layer. The model also says, think about congestion. That is to say, too much traffic to fit down the network that we've got right now. So you're all familiar with if everyone's hammering on a server, everything slows down. That's simply because there's too many packets trying to get through the network. And there simply isn't capacity, there's not bandwidth in the network to deal with it. This is congestion. The 7-layer model says, here's a good place to think about congestion. Maybe use multiple paths to get to the destination. So spread the load out amongst multiple different paths to the destination. These days the solution is using flow control. That is, there's a mechanism in the networking protocols that tell the source, slow down, don't send it quickly. Rather than trying they blast packets as fast as they can, and the network dealing with the problem, the network tells the people sending the packets, please slow down, I can't manage. Dealing with congestion in that way. So again, there are many solutions out there in the real world. But the model doesn't give any particular suggestion on which one you should choose. There's the opposite problem to congestion of what happens when you could go faster. Congestion disappears, you can start moving things faster again. So flow control says things can go slower, maybe you need to go slower, maybe things need to go faster. Network layer is supposed to deal with these kind of things. Also, in this layer, you might want to think about accounting. Accounting as in, we need to make people pay. Counting the number of bits so we can bill the user. The thing that most of you don't particularly worry about, in that you have a network connection and you just use it as much as you like, and there you go. But somebody's got to pay for all this. The 7-layer model suggests that this layer might be a good layer. In real life, it varies immensely where the bits get counted. It is very much less prevalent in real life implementations doing counting in the networking layer. So next layer 4, the transport layer. Except for the session layer, that is the layer above, are only in the packets. Much easier to understand the fancy word packetization. When you've got a big file with your video, your picture, your sound, whatever it is, it's one big chunk of bits. It needs to be chopped up into little packets. Everything is sent in packets. So at some stage, we've got to move for big chunks of data to packets. And this is the layer that does it. Also does the opposite. Packets coming up to the destination and get received. The destination has to glue the packets together back in the right order. This is depacketization. And it's taking packets and making your big movie once again. Packetization, relatively speaking, easy, because you just go chunk, no problem. It's the depacketization that's the interesting thing, because packets might arrive in different orders from they were sent. One packet might go a slow route, another packet might go a fast route and get there first. So depacketization, how do you know which order to reassemble the packets into the original file? So depacketization is the hard part here. In real life, the transport layer is quite different from this. It does the packetization and depacketization, but also in real life, as in the network, the internet, a lot of other stuff actually happens in this layer. Layer 5, the session layer, manages the sessions, connections, if you like, between source and destination. So a remote logging session, I sit down and log into somewhere. There's a long sequence of connected packets that go backwards and forwards, all part of this one logging session. But logging sessions are sessions, but sessions don't need to be long. They could be quite short. So you might like to think the transmission of a web page is a session. Could be arbitrarily long, could be arbitrarily sort of short. But it's essentially just some sort of a logically connected set of exchanges with some kind of unified identity. This is a very hand-wavy description because nobody has a real clear definition of what they mean by session. Different people understand different things. But it's a bunch of things that sort of go together. Maybe just a web page, maybe a 5-hour login session on a remote machine. But everything is related. The point about sessions is that every packet in a session are kind of treated in the same way. They're all going to the same destination, they're all being treated in the same way as they get to the destination. So sessions are supposed to have interesting properties, like suppose you're transferring a big file from one place to another and the network crashes. A little while later the network comes back. The session mechanism is supposed to spot the networks come back and say, okay, we were halfway through transmitting a file, and then pick up from where it stopped, and then carry on. So maintaining the session. It knows that it needs to continue the sequence of related packets, that is the rest of the file we want to transmit, rather than forcing the user to start again. Well, what happens if the network crashes halfway through your downloading web page? Well, it's gone. You have to start again. That tells us that the magic that we use for web pages doesn't do sessions. At least it doesn't do sessions like this. So sessions are things that the standard recommends you think about, but it turns out inside the internet, sessions are really not supported at all. Again, that's not an entire truth. That's a 90% truth. There's some small element of sessions in the internet, but it's not enough to pick things up from where they left off. If you're downloading something and it crashes, these days typically you have to start again. Unless the application knows that. So sessions, a bit of a fuzzy layout, fuzzy in the sense of not supported well in the internet, and people aren't really sure what a session is either. Next layer, presentation layer, layer 6. Here we decide on representations of our data. So how do we represent characters? How do we represent numbers? How do we represent colours? How do we represent sounds? All these kinds of ideas. So that source and destination can agree on the meaning of this bunch of bits that we've just received. I said previously that you've got all these different ways of representing integers, the signed and unsigned, and two complement, and all these kinds of things. Two machines, their hardware might have different ways of implementing integers. If I send the number 7 from one machine to another machine, they've got to receive the number 7, even if they represent it in a different way. I use this set of bits, they use a different set of bits to represent the number 7. How do we reconcile this? This is what the presentation layer is supposed to do. It's supposed to put things into standardized formats so that both ends can understand, oh, these bits mean the number 7. And then they can convert them into whatever format that they use themselves to represent the number 7. And similarly, colours, sounds, or every other kind of data. Different ways of representing characters and all these kinds of things. There are many ways of representing information in terms of bits. So here's what I've just said. You've got to make sure that presentation is there to preserve meaning of information. Meaning of information is different from the bits you use to represent it. Bits are just bits. What do these bits mean? This is what presentation is about. So I send you some bits, you receive some bits, we agree on what those bits were supposed to mean. Again, this is a concept that some people have difficulty understanding. You just say, send the number 7, it's a bunch of bits, isn't it? Well, information and representation of that information, there's a big gap between the two. We've got to make sure that everyone understands the meaning of the information, not just the bits that you happen to receive. Okay, so presentation layer turns out again not treated terribly well in the internet protocols. Topmost layer, layer 7, application layer. The application layer, well, you know what applications are. It's the layer application programmers deal with. And in there, there'll be various protocols to do the thing that you want to do with your network. So there's the HTTP hypertext transfer protocol that fetches web pages. A simple mail transfer protocol to transmit emails, all this kind of thing. Here, various protocols defined in various documents, and it's this layer that deals with these kinds of protocols. At this layer, we're not thinking about packets, we're thinking about here's my email, here's my web page as a whole. Represented in whichever way I find convenient. Somebody else's problem, the presentation layer, that is, to convert what, my web page into bits in some kind of sensible fashion. On top of these application layer protocols, you actually see the applications. So your web browser will be talking HTTP to a web server. Your email application will be talking its SMTP, single mail transfer protocol, to an email server, things like that. And these are protocols that describe the interactions between a browser and a web server, or an email reader and an email server. Please send me this email, please send me this web page, here's your web page. So, separate layers, each doing a different thing. And some of these things treated less well in the Internet Protocol, some of them treated very well, in the sense that some part, in particular session layer, completely ignored in the Internet Protocol. So when we've got our application, let's say our email reader or whatever, what's going to happen? The data for an application is going to be treated by the application layer protocol, wrapped up by this SMTP into something. Then that's going to be passed down to the next layer, presentation layer. The presentation layer is going to deal with a presentation, that is, how do we represent in a way that everybody can understand, how do we represent this information in terms of bits. Then that's going to go through the session layer, through the session layer, that's going to go through the transport layer, and so on. It's going to go through all through these layers. Each is going to do their little bit of the huge great job of transmitting information from one place to another. Then you can think of this as a sequence of bits of code. One bit of code to do the application, one bit of code to do the presentation, one bit of code to do the session. You can think of it like that. Again, in practical terms, you don't have to do it like that, as long as the effect is like that. And as your data is passing from layer to layer, it's encapsulated. That is to say, the data might get changed in some way, such that the layer below can cope with it transparently. That is to say, the different layer can't misinterpret what these bits mean. And then this transformation, this encapsulation, is going to be undoable at the other end. So start mixing up my data at one end, I transmit it, I have to sort of unwrap it at the other end. I'm going to give you an example of that, why that kind of thing is necessary in just a moment. But these encapsulations, these transformations, could be essentially anything. It could add an identifying header. Here's an email, put a header on it to say who is it from and who's it to. That's sort of understandable. Sometimes you could add a trailer, as is a thing on the end of it, rather than just a thing on the front of it. Something that the functionality of the layer. The mail transfer protocol needs to know who you send the email to. It's not part of the email, it's not the text of the email, it's something about the email. If you like, it's metadata for the email. But somebody needs to know it, who is this email going to, so it's going to be put in data somehow. Translation might be encode certain bit patterns that might be misinterpreted or mistransmitted by the next layer. The example I'm going to talk about shows that. Put items in a standard form. So here's an example of presentation. Converting integers from one form to another form. do some arbitrarily complicated manipulation, like encrypt it, where the bits that come out are completely different from the bits that go in. The other end of the scale, a layer might do nothing at all. Here's the bits, move on to the next layer. That is an empty layer, if you like. The layer actually does zero, doesn't do its job, but then, well, you've written the standard, so presumably that's what you want. What happens is you've got a little bit of your data, maybe your email or something like that. You pass it to your email, type it into your email sender. It's going to stick on an application header, for example. The application header might say to this person, from this person, date, this, that, and the other. This passes on the presentation, which might manipulate the data field and stick on at the header, saying, I have used this method for encoding data. Passes on the session, passes on each layer, does something, passes it on to the next layer. And so down the bottom, I've got a data lake which puts a header and a tray on it, for example. And then the physical layer is where bits actually get transmitted. So my original data may or may not look anything like the bits that actually get transmitted. It's all this layering and encapsulation, messing around with bits. It's possible, but very unlikely. You really wouldn't do it quite so like this. You could do it. In fact, some very early networks did do it like this, and not surprisingly, they were very, very slow because they followed the things to the letter rather than to the spirit. So there's an example of kinds of encapsulations. Why do we need them? Some of the early modems, again, go look at some old films that people have those things that dial up telephones, and they put telephones into little holders and they make funny scratchy noises. Modems. Treated byte values less than 32 as commands to modem. So when you're connecting to your remote computer, you send the command connect, you send the command disconnect, and things like that. Then when you say connect, here's my data, disconnect. The commands to the modem were small numbers. Data was data, whatever you want to transmit. For example, the byte value 4 would mean disconnect in transmission. It tells the system that it can take the network link down and then disconnect the telephone line, whatever you're doing. Modem should drop the connection. Seems fair enough. Well, you need something to do that. But the question is, what happens if my data that I want to send contains the value 4? I've got a bunch of numbers I'm going to send to the other end, and one of those numbers is 4. Well, I can't just send it, because it starts sending my data 7, 11, 13, 4, disconnect. But I can't send any more data. My data has been misinterpreted by the modem as a command to disconnect. So this is why we need encapsulation. You need some way of hiding the fact that I've got a 4 in my data stream, so that my modem doesn't misinterpret the data as a command. The number 4 is never seen in the data stream. This transformation must be reversible. So at the other end, when the bits come out again, stuff comes out. How are we going to make sure the other end realises that I sent a 4 here? You can't just sort of not send it or add on 23 or something like that. You've got to have some mechanism which is reversible. So this is why encapsulation is necessary. Data can be transmitted accurately even if you're using weird hardware. You don't want to have to know too much about the hardware, you just want to be able to send the data. In this particular example, they use something called byte stuffing. And the link layer would physically go through, before it passed the data to the physical layer, it said, oh, look through and say, oh, here's something which is dangerous. It looked through the byte stream and said, here's a 4. I'm not going to give a 4 to the modem because I know 4 would be misinterpreted. So it actually sends something different. Actually, rather than sending a 4, the link layer sends, for example, dB/d4. Hexadecimal values here, but convert that into decimal if you like, don't make any difference. It's just some magic number followed by an encoding of the number 4. Both bytes get through the modem, but they're not less than 32, they're not mistaken for data. The other end, the link layer receiving data from its modem, sees dB/d4 and says, aha, that actually meant the number 4, and unencapsulates it back into a single byte. So a 4 went in, a 4 came out, but a 4 didn't travel along the wire. So the dB here is called an escape character, very much related to the escape key on the keyboard. Escape character says, do something different here. Present means the next character coming along is special, needs to be treated specially. Not treated literally, so if I see dB/d4, I don't think I've got 2 bytes. The first is a dB, the second is a d4. It means to treat these 2 bytes specially. In this example, decode this into whatever. So a byte 5 might be encoded as dB/d5, a byte 6, dB/d6, and so on. So you ensure that no values less than 32 ever get sent. They're all byte stuffed or encoded or escaped. 3 different phrases for the same thing: byte coding, byte stuffing, encapsulation, what the other 2 which I've already forgotten I said, but they all mean the same thing. Now this seems fine, so you solve the problem of sending values 4 down the line, but you've actually introduced another problem. Suppose my data contains the value dB/d4. I want to send the 2 bytes, first is dB, the second is d4. I can't just send those 2, because the other end will read dB/d4 and think, oh, they make 4. They decode something that wasn't encoded. So you don't have only escape the values under 32 in this example, but you have to escape the escape as well. So you don't misinterpret the escape value as an escape character. And in this example, again, these numbers are pretty plucked at random. Many different easy codings exist. dB could be stuff as dBFF. So if I want to send dB/d4, I stuff the stuff, or I escape the escape, send dBFF and then d4. And now I've got 3 bytes when I wanted to send 2, but the other end says dBFF, that actually means a dB, and then it goes to d4 and doesn't try to decode that. So we get a trade-off here. Byte stuffing, we're sending more bytes, and certainly in the early days every byte was took a long time to transmit, so you needed to save as many bytes as you could, but the gain was you get accurate transmission of data. It's slightly slower, but it's accurate. You don't misinterpret certain values. Okay, a pause for 10 minutes there, I think. We'll come back at quarter to make sure you get correct transmission of data. So byte stuffing was a real thing, and people could actually misuse systems where they didn't do this right. If you go and again look in your history books about telephone phreaking with PH, there was a point in time where, before digital telephones, that systems were controlled by making noises down telephone lines. So you could speak, and that would be sort of the data stream, but the control of the system would be funny noises, actually tones. And certain tones would be correct and connect, and other tones would be disconnect when we come later. And it turns out that certain people could essentially whistle down a telephone line and then get free services out of the telephone system. is exactly the same kind of idea, in that you've got the telephone system having noises, both mean data and control of the system. Control of a telephone system, dial up something and connect to someone in Australia for free, that kind of thing. In a modem, it would be possibly less expensive, but telephone system didn't do any encapsulation of the sounds that went down. Well, eventually, people moved over to digital telephone systems, so we don't see any of this anymore. But do you ever hear one of those old touch-tone telephones? Those funny multi-tone things, that the sounds that they made. That was their attempt to just make it difficult for people to make the right noises to control the system. So here it's trying to get around the problem that data and control of the data were going down at the same channel, and one could be easily mistaken for the other. Anyway, so back to layers. Each layer has got its own little thing to do. Some of those little things aren't very little at all, but they each got a very well-specified task that they need to do. And they sort of all come together and make the transmission of information work overall. In the normal way, you have a big problem to solve, you chop it up into small problems and solve each one individually. So suppose we want to send an email. If we were following our specification absolutely to the letter, you might find that your email application adds a header to your email, a from field, a to fields, and so on. As I said previously, who it's from and who it's to is not part of the text of the email. It's part of what the system needs to know to control what to do with the email. So again, it's control information rather than the actual data you're trying to send. And then this is passed on your application to the presentation layer. Assuming it's a presentation layer. As far as the presentation layer is concerned, it's just received a bunch of bits from another layer, from the application layer. Presentation layer shouldn't really know that the first few bytes of the data it's received are actually application header. It should just say, I've got a bunch of bits, what am I going to do with this bunch of bits? It should be as ignorant as it possibly could about what those bits actually mean. Is it part of the header? Is it part of the body of the email? Presentation layer does not care. So at least it should not care in an ideal world. It might transform the information in some fashion. It's doing its job, the presentation job of making sure that characters are represented in a universally understood format or whatever. It might stick on its own header at the front. Say, presentation layer transformed using such and such a mechanism. So at the other end, when it receives this, you can say, oh, it used this mechanism, I know how to undo this mechanism to get the email back. You might do this. This might then be passed down to the session layer. And again, the session layer is receiving a bunch of bits from the previous layer. As far as it's concerned, it's just a bunch of bits. No further information should be necessary. It shouldn't know that the first few bits of the chunk of data it's received might be a presentation header, or it might be something else. It shouldn't have to know. All it should know is how to do its own job on a bunch of bits. It does its job, and that might be involve transforming the bits in a certain way. It might be sticking a header on or whatever, but it does whatever it needs to do to support sessions. And then it passes it down to the next layer. And the next layer, dot, 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 does the same kind of thing. Each time a layer gets something from a neighbouring layer, it should just treat it as a chunk of data. It should not know anything about what that data means, as far as is possible. I keep using this phrase, as far as is possible, because, again, in real life, you do have to fuzz the boundaries a bit, and you do have to have a little bit of knowledge between boundaries and stuff like that. But practically theoretically speaking, you want everything to be neat and tidy as possible. You get down to the physical layer. The physical layer transmits some bits. How it does that? Well, it's up to the physical layer. Destination receives some bits. And at the other end, you've got another sequence of bits, of chunks of software, which will do the decapsulations, reversing all the stuff that we've done. Unwrapping and untransforming as we go, sending up to the next layer, sending up to the next layer. And again, each layer should just receive a bunch of bits and do whatever it needs to do to decapsulate it. And eventually, we get to the application at the other end of your email system, which should receive the text of the email. Or at least something that the other end interprets as a text of an email. But this is, as it says, we hope, is what happens. And these days, mostly, this is what does happen. Certainly in the earlier days of the internet, things went wrong all over the place. And didn't neatly decapsulate, or bits went wrong or was overshot, but at least you can be happy that it mostly works these days. But you might be sitting there thinking, this sounds so terribly wasteful in time and process of time and messing around and bits of code you have to write and all this kind of stuff. If our original email was really short, let's go down the pub, yeah, nice a dozen or so characters, nice short email, goes through all these layers, adding headers, doing stuff, adding headers, doing stuff, adding headers. You might find that the bits that actually get transmitted are mostly overhead. Your data might have been short, but by the time you've added all the headers for all the layers, most of what actually gets transmitted is this other stuff. And so we've sort of multiplied up a small thing into one big thing that needs to get transmitted, rather than just the email. There's got all this other stuff as well. So this sounds very wasteful. Why don't we just put the data on the wire, send the bits of the text of the email. There you go, and you're sending much less data, it'll get there faster because there's less data to transmit and all this kind of stuff. And the reason we don't do this is because, it's fraught with errors and flexibility is the main thing. And it comes down to, again, this idea of modularity, that if we're just sending the bits on the wire, my application has to know how to put bits on a wire. My application is not doing the game, it's just putting the bits directly on the wire itself, skipping all the stuff in between. Suppose we're running on we've got a 1 gigabit network, and someone comes along with a new standard and says, oh, this is 10 times as fast. And you say, gimme, I want this on my machine. Because of the way layering works, the physical layer, as far as possible, is pretty much independent from the next layer up, the data link layer. And so, the part of your standard that describes how a 10 gigabit network works is very, very easy to put in the standard where you have the old 1 gigabit network description. Very easy, just sort of say, oh, it's in this chapter, wherever I see 1 gig, cross it out and write 10 gig. There you are, you've got your new thing. Of course, talk to electrical engineer about the difference between 10 gig and 1 gig, but there are all kinds of other issues, but you've localized it to one chapter in the specification of your standard. And similarly for the implementation, you've got a bit of code that deals with the 1 gigabit network card. You modify it a bit to make it talk to the 10 gigabit card. It's isolated. This is all really, really standard software engineering. You isolate things that when you need to make changes, you make changes locally, not all over the place. The upper layers don't need to know anything's changed. I've changed something down in the physical layer, and certainly everything above the data link layer does not have to change at all. Maybe the data link layer has to change a bit, because it's now talking to a different physical layer, but that's, again, local based. So, We don't have to go back to our application, indeed all our applications, and rewrite our application. Because the code's not in the application, it's in the data link physical layer. We don't have to get a new browser simply because you've put a bit of new hardware into your computer. Again, it sounds obvious, but these things don't happen by accident. And it's similarly for all the other layers. If we decide that we want to replace an implementation or a standard description of a layer by some other thing, we take out the old thing, put in the new thing, and the neighbouring layers, all the other layers, can remain the same. You don't have to mess around with the rest of the stack of these layers, because you kept everything localized. And in principle, you could use carrier pigeons as a physical layer, and your browser should work unchanged. Nothing in your browser has to change simply because the physical layer you chose has changed. Might go a bit slower, so there might be some sort of a obvious effect of what's going on, but someone actually did do this once. They got the bits coming out of the link layer and wrote them down with little bits of paper, tied it to a pigeon, sent off the pigeon at the other end. The decapsulation was getting a bit of paper off the leg of the pigeon, typing in the bits, and then goes back up through the leg. Oh. The way it really does work. Thought it was massively slow, but it did work, which is the issue. Go away and read some RFCs about this. 1149 and 2549. They describe changing physical layers for slightly more frivolous physical layers. But the fact is, everything still worked. Your browser didn't have to change. The networking code, the TCP/IP code, didn't have to change. Because it's all kept separate. And there are many other places inside the internet where the fact that we've got layers means other things work really well. If you know about VPNs, that's all based on layering. If you don't worry. Okay, so layering is a good thing. It's an important thing. As I say, it's a factor behind the way the modern internet works. There is a question of why 7 layers? 7's a nice number. History gets a bit vague at this point, but it seemed that mostly that IBM, big computer company at the time, had their 7-layer thing, and they managed to convince the people on the ISO standards committee that this is how you should do it. 8 is too many, 6 is too few, 7 is just right. IBM in those days was the biggest computer company in the world, and so they had a bit of a clout in describing this. They said this is a good way of doing it, most people believe them. Not sure who's the biggest. Is Apple still the biggest, or is it whoever? But biggest purely in terms of money these days. I'm not sure what the right criteria to use for saying the biggest company. Well, so 7 was for a long, long time just the right number. Other people say 7 is not the right number. Particularly if you go to talk to electrical engineers who have to deal with the stuff down in the physical layer, they say having a physical layer is not fine enough. They want to subdivide it. They want to split the hardware layer into finer layers. Because the bit of wire and then you have the electrical signals on the wire. They're two different things. And they want to treat them differently. Other people say 7's a big number, can't cope with 7. They want fewer layers. An example of this is the Internet 4-layer model. Because 7 has lots of stuff in there that nobody's interested in. Let's chuck out the stuff we're not interested in. Well, in their argument. So the Internet 4-layer model developed after the Internet Protocol had gained prominence. So I said that this was a case of making the documentation match the implementation. Because at this point, computer scientists were saying a layering model is very important and the right way of doing things. People sat there using the internet saying, well, I suppose we better invent a model file that describes our system now. And surprisingly, because the internet essentially has 4 layers in it, they came up with a 4-layer model. Link layer, network layer, transport layer, application layer. So names very reminiscent of the 7-layer, but a bunch missing. Physical presentation session. Yeah. So 4 different layers. Oh, yeah. And sometimes called link layer, sometimes called data link layer. It's not important which. It's the layer that links you to the next machine. So a 4-layer model. And of course, each layer, well, either regard this as simpler because you've got 4 rather than 7, or regard this as more complicated because you've got everything to stuff into 4 layers. So each layer is going to be more complicated. In practice, don't use this model. Stick to the 7-layer. Anyway, so we need to describe this model, and at the same time, we'll describe TCP/IP. TCP/IP, of course, is the standard. 4-layer model is the model. TCP/IP, 1974. That's when it sort of first came out well, under that name. There were experimental things before that, but TCP/IP, 1974. So then the model, as I say, came out later, when they decided that they needed a model. They don't really need a model. Take care to distinguish between this model and the instance of the model, the model and the TCP/IP standard. So again, they're very easy to confuse because there's a one-to-one mapping, because they just relabeled, took the bit off the TCP/IP that said TCP/IP standard and replaced the word standard by the word model. They get very confused as they're very similar. Possible, if you're very stupid, very unlikely, there could be another networking standard that followed the 4-layer model. But you're not going to do that because we've got one that works already, and it's called the internet. It's not a very good model, as I keep saying. It's not. It's both not fine enough and too few layers. If it ever came to that very unlikely thing of we turn the internet off, throw it away and start again, we'd be very wise to follow the ISO model, the 7-layer model, much more closely than the internet does. But again, that's not going to happen. So in this world, we've got the ideal theory and the practice, and there's essentially they miss each other completely. So the 4 layers of the internet model. Link layer. Link layer corresponds to the ISO physical plus data link layer. So anything that isn't software goes into this layer. Plus some stuff which is software goes into this layer. So if you're thinking of the internet, you just think, oh, there's something that sends packets. And that's about all they say. It's a very underspecified model. It has to be capable of sending and receiving internet protocol packets. It really, as a model, as I say, this is not terribly helpful. It just says, it's whatever you need to get the thing working. Conversely, this does mean that the internet runs on an awfully large numbers of different kinds of hardware. Because the internet doesn't really rely on any specific feature of hardware. It might be running on Ethernet cable, it might be running on Wi-Fi, it might be running on carrier pigeons. As long as it can transmit packets, that's what we really need to know. What you do with your hardware is pretty much open. It doesn't solve the problem for the engineers who have to build the things. They go back to their refined model, their refined 7-layer thing. They supply data link, link into more one layer, and the physical is more one layer. But then, we're not anyone electrical engineer? Okay, I can be rude then. So they can do whatever they like, as long as they give us hardware that works. As computer scientists, we want to be able to send packets, and that's the entirety of the specification. Well, I suppose send and receive packets, it would be better. But much more than that. Well, the Internet Protocol doesn't rely on any specific feature of what these packets do. So we do find lots of widely varying implementations out there of physical things. Probably familiar with Wi-Fi, maybe familiar with Ethernet, but there's cellular phones, there's optical things, there's ADSL and VDSL which you have going into your house, all these kinds of things. They all, at base, can send packets, and that's all we need to do for us to be able to put the Internet protocols on top of them. Okay, next layer is the network layer, and alternate name is the Internet layer. So if you want to confuse someone, you talk about the Internet layer in the Internet protocol. Another stunning lack of imagination for naming things, but this does the same as the network layer and the 7-layer model, particularly routing. Routing is the way you connect one network to another network. Which direction should this packet go in? Routing is the major issue to be solved in this line. Corresponds directly to the ISO 7-layer network layer. In terms of implementation, in terms of the standard, in TCP/IP, we've got the Internet protocol. That is to say, a protocol called the Internet protocol. So again, we've got yet another confusion in that in the Internet model, we have a layer called the Internet layer. In the TCP/IP protocol, the Internet protocol, we have a protocol called the Internet protocol. Plenty of opportunity to get confused about what we're talking about. The Internet protocol. It's a protocol within the Internet protocol series of protocols. IP, that is the network layer protocol, is what's called an unreliable protocol. This is a technical word. It doesn't mean to say it is definitely bad. What unreliable means is it's not guaranteed to be good. Again, this actually turns out to be an interesting choice, because we don't require reliability from anything below us. We don't require reliability from the hardware link layer. So even if we have an unreliable physical transmission, we are still going to be able to do our job. We can still build the Internet protocol on top of it. Even if the hardware is unreliable, we can build something out of it. So even if your pigeon gets shot, your browser should still work. So unreliable protocol. This idea of reliability is one of these things that you start off thinking, well, it's got to be reliable, isn't it? But then eventually you come to the idea unreliability can be a good thing. Sometimes it's better an application to deal with the occasional lost packet, or maybe corrupted packet, than try and stop everything, say, give me the packet again, get it resent, and then carry on from where it stopped. The mechanism to deal with reliability can sometimes be more disruptive than dealing with the unreliability. The usual example of this is a video stream. When you're watching a video stream, if a packet gets lost, well, maybe that means a slight glitch on the picture. And the eyes will say, oh, there was a glitch, and then you don't think about it. Rather than stopping the video, getting the thing to retransmit the frame, then starting up again, and you definitely notice that. In video streaming, fast delivery is more important than accurate delivery. Again, these things are a little surprising the first time you come across them, but it turns out you'd rather have the occasional glitch rather than stopping and starting and stopping and starting and having perfect features. So it's actually quite useful to have unreliable mechanisms sometimes. That is to say, not guaranteed reliable mechanisms. Because they're useful. In terms of physical hardware, much of the internet hardware these days is fairly reliable. Certainly all the copper wires and optical fibres and all these kind of things, pretty reliable. Wi-Fi, a lot less reliable than you might think. You can have tens of % of corruption in your packets. If you're stood next to a microwave, there could be lots of interference of your ping dinner with your browsing. There's a lot of wireless interference that goes on. Copper wires are a lot better, but still there is some interference. But again, the important thing is we don't have to rely on the fact that our hardware is 100% perfect. Because we know in the real world, no hardware is 100% perfect. So, next layer, transport layer. Very much like the ISO transport layer. Providing a flow of data between source and destination, and in particular dealing with this packetization and depacketization. So it does, well, not all the OSI model says, but it's the how do I glue the packets back together in the right order. It turns out that in TCP/IP there are two major protocols. In fact, there are more than this, but there are two big ones in this layer. That is, two protocols, two ways of doing the transport layer's job. Then you get the choice. When you write your application, you get the choice of which. Transmission control protocol and the user datagram protocol. So TCP and UDP. two choices. And the choices are there because one's reliable and the other one's not reliable. TCP is a reliable protocol. It guarantees delivery. When you say guarantee, you can't actually guarantee 100% reliability out of anything in the real world, but as far as is possible, it will get the packets through uncorrupted. Doesn't mean that because it's on top of an unreliable layer, the internet protocol in the network layer is an unreliable protocol. Things can get lost, things can get corrupted. TCP reliable, built out of an unreliable thing. So there's got to be some kind of a mechanism for building reliability out of unreliability. The mechanism is very interesting and far too complicated to go into right now, but a mechanism of packet acknowledgements. Right? Here's a packet, got it, here's a packet, got it, here's a packet, got it, back down. So every packet is acknowledged as being received and correct. That's what when it goes wrong. That's the interesting part. But fortunately for you, we don't have time to go into that right now. But it's an expensive mechanism. Essentially, there's got to be acknowledgements, that is more data going backward, every day for data going out. There is an overhead to pay for having reliability. And sometimes we don't want to pay that overhead. Sometimes we just want to say, go as fast as you can, don't care if there's an occasional error. Video streaming. So this is why the other protocol exists, UDP. It's a non-reliable or unreliable protocol. It just says, here's a packet, here's a packet, here's a packet. It doesn't have any of this clever acknowledgement mechanism. So it has no mechanism for building reliability. And in fact, it is reliable or unreliable as the thing it's built on top of, the network layer, IP. So it doesn't try and make it better in any sense. If your IP layer is apt to be reliable, then your UDP will be reliable. If it's not, it's not. But with TCP, don't care what the reliability of the network layer is. TCP is always reliable. UDP, it turns out, it came along a lot longer after TCP. TCP was invented because people wanted reliability. Those that thought they wanted reliability. So for a long, long time, the Internet protocol set was IP in the network layer, TCP in the transport layer. And that was it. Because everyone thought reliability was essential. A lot later, people came along and said, actually, unreliability is good as well. So we invented this much simpler protocol called UDP. Because it went faster, but the trade-off was you lost reliability. And again, this goes way back to the naming of the entire protocol set as TCP IP. Because that's what it used to be. TCP on top of IP. That was the entire story. These days, it's UDP and TCP and some others on top of IP, but the name is stuck. In fact, you really ought to call it just the Internet Protocol and be done with it. But you can't change people's minds. The names. So that's the transport layer. Next, we've got the application layer. And the application layer does everything else. And anything we haven't mentioned so far has to be done in the application layer. So, roughly speaking, that covers the session, the presentation, and the application layers from the 7-layer model. In particular, that means it's the application programmer. It's their problem to deal with anything to deal with session, anything to deal with presentation, on top of whatever the application actually wants to do in the first place. The application layer, well, it's got to do what the application wants, like send the email or send the web page or whatever it wants, but it also has to do in your program that the programmer writes. You have to deal with presentation, you have to deal with session and stuff like that. It doesn't kind of come for free. In the 7-layer model, you've got to do it. And because the programmer has to do it, the programmer frequently forgets to do it. And this was, again, evident in the early days of the web, where you had web browsers being written by one company, web servers being written by a different company, and they didn't get together and make sure they were interoperated. They didn't think about presentation. A server was producing web pages that web browsers couldn't understand, simply because they used different data representations of things inside web pages. Because the internet does not deal with presentation, applications writers didn't think about presentation, and when you use one browser with one company, a server, another company, it just got garbage coming out because they didn't agree on what the meaning of things were. These days, things are a lot better. Even big software companies who like to think they're in the universe, they still follow the standards because they know it's their benefit that everyone talks the same language. Okay, so presentation, not done in the Internet protocol set. If you want presentation to be done, your application has to do it. Similarly for the session layer. If you want the benefits of a session there, like a persistent session, and it's persistent in the sense that something goes away and it comes back again, you just carry on from where you left off. If you want that, you have to code that for yourself inside your application. It's not something that the mechanism behind the scenes does for you. If you want a persistent login, rather than something crashes and goes away and you have to start up again, well, your login application has to deal with that itself. It doesn't come for free from the other layers, but it's not there in the Internet. Some other protocol suites, ones which aren't used anymore, they did have these kinds of things. And so application could be just the application, and presentation and session was dealt with by the networking software. But Internet, they had a different, I'm really going to say the word choice. It probably wasn't a choice. It's probably out of ignorance that they didn't even think about it, that they didn't do it. In a typical implementation of TCP, the Internet Protocol, you have a wide varieties of physical link layers. Ethernet, Wi-Fi, cellular, these are sort of hardware things. ARP is a protocol we'll be talking about. In the Internet layer, you've got the Internet Protocol. That is the protocol whose name is Internet Protocol, and various other bits and pieces to do control. ICMP, Internet Control Message Protocol. And notice here that here we've got a distinction between the data we want to send and how to control the way the network works. Well, is that a good idea? Oh, go and whistle down the telephone line. If you have one protocol that does two things, then you have the possibility of confusion. Here we've got a protocol for data and a separate, different protocol for control of the way the network works. Yeah, so they learned their lesson about confusing control of the data. In the transport layer, we've got TCP and UDP and others, mostly experimental, but maybe in the next few years you might see some interesting developments in there. Reliable, unreliable data transmission protocols. In the application layer, we have hundreds of application protocols. Every protocol, every application you might think of probably has got its own. It doesn't live on top of the web. So mail transfer, file transfer, web page transfer, all these kinds of stuff. Application layer protocols. So this is what you would see if you went out there and stared at a computer. It is quite different from the theory where you have 7 separate layers, each with a specified function. But we still have a layering going on. Layering still works for us. So HTTP, Hypertext Transfer Protocol, the protocol says, fetch me a web page, here's your web page. It doesn't need to know anything about the hardware it's running on. It doesn't have to know whether it's Ethernet or whether it's a carrier pigeon. It doesn't have to know. It doesn't have to know whether it's running over TCP, IP, or some other protocol. That's becoming a bit more confused these days. Not that it's likely to be running on anything else than the standard that everyone else is using. Again, it doesn't have to know, and in the real world it's not likely to need to know, but things can change. So you tend to have a very much simplified picture of what's going on with 4 layers. Data, maybe your email, whatever. Then in the transport layer, there'll be a header to deal with the transport issues and all this packetization stuff. In the network layer, the internet layer, you've got an IP header. That mostly deals with routing. Where is this packet supposed to go? And then down in the link physical layer, we have, for example, Ethernet as a header and a trailer. So this is the start and this is the end of the packet. So this is very much more likely what you're going to see if you open the lid of your computer and looked inside. You see a 4-layer thing going on. On the left, I got same information again, really. Application layer, TCP and UDP in the transport layer, IP as a data transmission, and a variety of control protocols. There's ICMP, there's IGMP, there's all those kinds of things. And then hardware, you've got the hardware itself, be it wired or wireless, but then there are a couple of other link layer protocols that we're going to need to be talking about to deal with how the hardware works, management of the hardware. Okay, so we've got two layering models, and the one on the right corresponds to reality, the one on the left corresponds to theory. And matching them up is not a terribly clean match between the two. 4-layer model, you've got the link layer corresponds to pretty much the data link and physical layer. The network layer does the network layer. The transport layer does a transport layer. As it turns out, tiny smidgen of session, but not really enough to be called a session. Application has to do everything else. If you want to deal with presentation, if you want to deal with session properly, you have to do it in your application. Means the programmer has more work to do, and therefore more chance to get it wrong. So, theory and reality, kind of, but kind of not matched. Okay, so I'm running an example of email being transmitted over an Ethernet. We're going to start with the text of our email inside our application, and our application is actually going to deal with presentation issues. So let's make sure that if the two ends have different representation of characters, you can get the text of the email, not just some random selection of bits. And the application transforms the text using a protocol called the Multiple Purpose Internet Mail Extensions encoding. Go look this up for yourself, but it's a way of doing presentation. But you have the mail application writer has to explicitly invoke the library to do this. The email application adds an envelope header. Called an envelope header because it's email, you stick it in an envelope, and this would be the from fields and the to fields. And if you're awake, you realise it's doing presentation, then application header. Not application header, then presentation header, is what we thought from the picture. You thought application header, presentation header. Well, so real life is far from perfect. It does it the other way around because it's more convenient to do it that way around. The email application has its envelope and then passes it over to the TCP software. TCP software typically inside the operating system chops the data into packets. The email chops it into bite-sized chunks, and each packet has to be identified with a header. The header is there to deal with this reliability thing and to deal with this repacketization, depacketization, whichever, gluing things back together in right order at the other end. It's a fairly complicated header that TCP has to run. It passes off to the IP software, which adds its own header. Most of the job of the IP layer is to deal with routing, which way the packet goes, and then passes it on to the physical layer. In this example, we're talking about Ethernet. And this puts on its own header to say, where's this packet going next? Starting from this machine, needs to hop to the next machine. What is the next machine? It's a physical layer header. That adds a trailer, as a checksum. That is an error detection mechanism to detect whether there was an error or not in transmission. If there's an error, then Ethernet doesn't do a retransmit or anything like that, it just drops the packet. So again, this is very different from what the 7-layer model says. And then, just to scare you, bits are transformed using 4B, 5B encoding, smooth bit patterns, and sent using a 3-level electrical coding, MLT3. You don't need to memorize any of that, apart from the fact that what actually happens in the hardware is really, really scary and complicated. It's not just a simple, here's a 1, here's a 0, 1 volt, 0 volt. It's very, very, very complicated. There's all kinds of transmogrifications or bit patterns and other bit patterns, and it's not a 2-level thing in 100-bit and megabit. It's a 3-layer thing, three different voltages, and it's not the height of the voltage, it's the transitions, and it's all very complicated. And then we get off to gigabit networks, even more complicated. These things are not simple at all. In fact, Yeah, probably the most complicated part of the whole suite of protocols is how physical things do their job. But go talk to an electrical engineer if you can't sleep. But anyway, so it's kind of simple. You see each layer doing a specific job. You've got stuff that the application needs, stuff that the reliability needs, stuff that the routing needs, and then stuff that the hardware needs. And by having layers, every one of these is isolated as much as possible from every other layer. So going back to these two models, if you've got two models, you need to compare them. The OSI model was developed before implementation. Internet model created after the implementation. So as I say, Internet model was documenting something already existed. Whereas the OSI model was, here's the theory, why don't you go away and follow the theory. OSI makes a clear distinction between model and implementation. At OSI, you can see this is a model. With Internet, it's very fuzzy when you talk to someone. Are you talking about the model or are you talking about the standard that follows the model? And most people wouldn't even understand the distinction between model and implementation. OSI general can apply to many networking systems. Internet model is very specific. You wouldn't use it to describe anything other than the Internet standard. And there's a very good argument for saying the Internet model shouldn't really exist at all because it's pretty useless. To describe something you already know the description of. Implementations following OSI model were dire. People had the theory, they went away and followed the theory to the letter, and the networking protocols which developed out of those were absolutely appalling. They ran really, really slowly. Meanwhile, people using Internet protocols saying, what's the problem? Our network goes really fast. TCP/IP widely successful. Probably don't even know the names of other protocols out there. There were some, but they weren't successful. That's probably a good place to stop. We're going to be talking about that, so you understand what all those letters and words mean. Variety of speeds. Original Ethernet was 10 megabits a second, which isn't too bad considering in those days in 1982 that was really quite a fast network. But these days it goes very much faster. You can buy stuff going 100 gigabytes per second, gigabits per second these days, and they're still working on making faster versions. Certainly they're looking at 400 gigabits and maybe even terabits per second for Ethernet. So you really need to explain what this CSMACD thing is. And it's hard to understand it, we just have to look at what the hardware does for it. Does for us. It's the multiple comes from the fact that Ethernet is a multiple access medium. That is to say, multiple access is just another way of saying shared. Several hosts share the same physical bits of hardware. And certainly in the original Ethernet, they just shared a single bit of cable. There was a big fat bit of cable into which you plugged your hosts being computers. Certainly in them days there were only computers. But the idea of sharing the thing connection between them. Sharing is good because it's cheap. Sharing is bad because you're sharing. A given amount of bandwidth available on the network has to be shared by all the hosts that might want to share it. But it turned out that being cheap was very much more important. And this is why Ethernet took off so well, because compared to all the other networks out there, it was very cheap and it worked reasonably well. Anyway, so sharing multiple hosts sharing the single medium. So A talks to B, it puts a signal on the wire. C wants to talk to D, it puts a signal on the wire. But unfortunately, the way electricity works, if A is talking to B, then C can't simultaneously talk to D because the signal occupies the whole of the shared medium. Go talk to a physicist or an electrical engineer about electricity, but as soon as you put a signal anywhere on the wire, it's sort of all everywhere on the wire. So if two hosts try and communicate simultaneously, like A to B and C to D, there will be a collision of their signals. Now, that is to say, you look at the electrical signal on the wire, it will be a mixture of the signals from both the communications. The one from A to B and one from C to D, they'll get mixed up and therefore corrupted. Certainly in those days, there was no way of sort of unpicking the two signals from each other. You either got a clear signal and then you've got your data, or it was corrupted and you've got no data. So to avoid this, this is the first part. A host will listen to the shared medium to see if anyone else is sending a signal right now. Carrier sense. Carrier is the thing that carries the data. So, is anyone else talking right now? Silence? No, okay, it's okay. Good for me to talk right now. Someone is talking right now. I don't try and talk because it's pointless me trying to talk over somebody else. I won't get my data through, and you'll just make their data get lost as well, lost and corrupted. So carrier sense. Before you start speaking, you listen. There's another moral for life for you, but don't talk over other people. Then continue listening until the medium is free, and when it's free, then you can start transmitting. Sounds sort of fair enough, doesn't it? Only transmit when you know, or when you think the medium is free, the shared medium is free. And that sounds fine, because then you start sending your data. But unfortunately, it's not quite enough to make everything work. And I'm sure you've had this in human conversations as well, that if A wants to send a signal at the same time as B wants to send a signal, what might happen is they both listen, they both hear nothing, they both do their carrier sense thing, they both hear that the medium is free, and they both think, okay, it's okay for me to transmit. They both listen, they both hear nothing, they both send. And you still get a collision. Even though when they were listening, there was nothing there, when they started transmitting, there was something there. Again, in real-life conversations, you might have this problem. Two people start talking simultaneously. That's a problem. So, simple carrier sense is not enough. What you have to do is keep listening whilst you're transmitting. Collision detection. Continue to listen while sending to make sure that nobody else has started talking when you were talking. Collision detection says there were no, well, determine if there were any collisions whilst I was sending. And if there is a collision, well, it's pointless carrying on. Your data has been corrupted, your signal has been corrupted, therefore your data has been corrupted, therefore you just might as well stop if there's a collision. Spotting collisions is fairly easy on Ethernet in the sense that you just look at the electrical signal on the wire. And if the signal you read off the wire is the same as the signal you're putting onto the wire, well, that means nobody else is putting a signal onto the wire. If the signal you read off is different from what you're putting on, that means somebody else is interfering. That is a sign of a collision. This is sort of nice and easy, and it's the benefit of using wired technology, that collisions are easy to spot. And it turns out that when you're using Wi-Fi, collisions are not easy to spot. And so Wi-Fi actually has to do something different. But anyway, if you're sending a signal, and while you're sending a signal, you carry on listening to make sure nobody else is interfering. If you detect a collision, stop, because there's no point carrying on. And then this is sort of one of the clever bits. You stop, you wait a small random period of time, and then start listening again for the carrier sense. Presumably, the other person on the other conversation is doing the same. They're listening, they're hearing the collision, they stop, and they pause a small random period of time before starting with carrier sense. But the point is, they'll probably wait a different amount of time before listening again, because they're both random periods of time. As is to say, a second collision is much less likely in the fact that I'll pause and you pause, maybe I start listening first, I hear the thing is free, and then I carry on, and then you start listening, you find out that I'm talking. So the fact that there's this random gap in there means that essentially you're tossing a coin to say who gets to go next. And you go back and start again with a carrier sense. This is important because there might be yet a third person on the network who stops listening after both of you stopped, hears nothing, and then starts. So there's all kinds of extra complications when you have multiple hosts on the network. So randomness is there to sort of arbitrate between two hosts trying to talk simultaneously. It also gives a small amount of fairness to a system. You toss a coin to say, is it you or is it me that gets to go next? Next time round, the coin might fall the opposite direction. There might be some amongst you who realise that there are ways to game this system. If your implementation of Ethernet doesn't wait a long random period of time, it's a short period of time, and maybe you get in first, which may be your traffic, it biasing the coin certainly comes up your way more often. This is certainly possible, but this would have to be built into the hardware. And if that was true, then that bit of hardware would be very suspicious. You wouldn't want it in your system. But anyway, hardware tends to be nice and fair. The way it does it. So here's the process, CSMACD. You start, listen until free. It might be immediately free, but you listen until free. You start sending whilst continuing to listen. If there was no collision, then you sent your signal. If there was a collision, stop, wait around a period of time, and then start listening. It's just sort of quite a nice and simple protocol. The lower one didn't have this listen to until free part of it. So it was just, this is just a bit more safe. Anyway, so you've got that. That's the protocol CSMACD. The actual hardware itself developed a lot over the decades. Original Ethernet was big fat cables. A big fat cable, the shared medium. Literally big fat cable. Kind of this thick. A coaxial cable. That is to say, same as the aerial cables come down from the TV aerial. A big fat copper centre with a bit of wire mesh around it. That was to give it good electrical properties. The mesh was sort of a protection against extraneous electrical signals coming in and messing up the signals. But it's big and heavy. Connecting your machine, your computer, to the Ethernet was one of these kinds of cable. A drop cable, and here you go. Just feel that and pass it round. That would be dangling out of the back of your machine. They don't get to see it at all. Okay, dangling out back of the machine. And but for some reason, I'm not sure why, but the coaxial cables tended to be yellow, whereas these cables used to be grey or blue. Goodness knows why the colour matters. But that would be plugged into your back of your machine and into something called a vampire tap, which would be a box clamped around the coaxial cable, and a spike in it, which you'd screw down, and a spike would go through the thing and touch the core of the coaxial cable. It would be a bite into the cable. And this is the way you connect your machine into the shared Ethernet. Very heavyweight, literally and metaphorically. But this was called 10 base 5. 10 was the data rate, 10 megabits. Base is baseband signaling, don't worry about that. The 5 was maximum 500 meter segments. 500 meter segments is the longest it could be. Again, a lot of this was driven by the electrical capabilities of the things engineers could build at the time. If it was more than 500 metres long, the electrical signal would degrade so much you couldn't get a clean signal out of it. These kinds of things. This is called Ethernet. Later on it was rechristened thick Ethernet, thick for thick cables. And there are all kinds of funny limitations on how long the drop cables could be, and how long the Ethernet cable could be, how many and how close these could be. And you really needed a degree in Ethernetology to understand how to build one of these networks. You just simply couldn't put things in where you liked. You had to measure them out and put them in the right places. Later on, fairly soon afterwards, it was replaced by thin Ethernet. Thin Ethernet because the cable is very much thinner. And you can see this is actually so much easier to use. In fact, the thick Ethernet was a massive pain on installations because you can't really go around corners terribly well. And nailing it to the ceiling was a problem. So thin Ethernet, very nice stuff. This is very much close to the kind of cable you might find in a television aerial, bring the signal down from the aerial down to the back of the TV. Does anyone have old-fashioned TVs with aerials anymore? Or is this so last century? Anyway, so this is smaller, electrically speaking, much more better tolerances. On the end, they've got nice connectors, and then you've got these T connectors that connect a single wire into your host. So the drop cable now doesn't exist, you just have this right in the back of the machine. This is great. It's got very much less likely the cable's going to fall out the back. The big problem with those cables is that you came in the morning, the machine wasn't working, you went look around the back, the thing had fallen out. Big problem with this, you came in the morning, the network wasn't working, is because someone up the line had unplugged their bit, and rather than pulling out the T, they pulled out one of the side bits, therefore disconnecting you from the rest of the world. Yeah. Bit for the weight. 10 base 2 was it's called, 10 megabits again, same speed, 200 meter segments. The length of the segments from here to here were shorter, but that wasn't such a problem. It's actually 185 meters, but 10 base 1.85 wasn't really a good marketing term, so it turned into 10 base 2. Much easier, much cheaper. Oh yeah, BNC, British Naval Connector, as in ships. Why they chose those? Probably a good idea at the time. Maybe they were cheap. Then reasonably shortly after that, technology moved on again to something that you might recognise today, where you have, rather than a medium being shared by things plugging into it, you have the medium being shared by a box you plug into. So now you have a box connected to the back of your machine by an Ethernet cable that you might recognise. What are these kinds of things? I don't know if you need to see that at all, but I'll turn around. The box was a hub or a switch, and I'll talk about that in just a second. And the bits of wire twisted pairs. There's 4 twisted pairs. Twisting them, again, is an electrical thing. The rate of twist is important, but means immunity against extraneous signals from other pairs of wires. Max 150 metres, again, all kinds of rules and restrictions. 10 base T, 10 megabits, the same speed, T for the twisted pair. This is pretty much where we are today still, where you have a box connected by bits of wire with hosts. And if you walk around the university, you'll see lots of these, well, you won't see them because they're locked away in cupboards, but there are lots of these boxes all over the place, and lots of bits of wire coming out the backs of PCs and training all over the place. So these hubs, or these switches, hubs were the first thing that came along, the earlier technology, and essentially they were electrical repeaters. A signal went in, the same signal went out on all the other ports. So the port there, a port there, a port there. The same signal goes in there, it comes out, repeated everywhere. So this means that everywhere has still got this shared medium kind of thing. Everybody's sharing the network. Switches, originally a lot more expensive, but these days very cheap. They were more intelligent in that only sends the signal out on the wire that the destination is on. And it's to say, rather than just saying everyone gets everything, the signal needs to go to a particular host, only goes out on one wire, not every wire. So in a picture, a hub repeats the signal to everybody. The hub doesn't know where the destination is, so it just sends the same signal to everybody. Whereas a switch says this packet is only going to that destination, so only send it out on that bit of wire. This packet is only going to that destination, so only send it out on that bit of wire. This is actually a lot more sophisticated because the switch has to know where each destination is. A packet comes in from somewhere, it has to look at the packet, decide where the destination is plugged into, and send the signal out on the right wire to that destination. The signal needs to read and understand packets. And this is why they were originally a lot more expensive. But these days, you're very likely to find hub in the shops. It has to look at the addresses on the packets. Read the addresses and say, okay, I know this one, it's over there, it's on that port there. And this is more problematic than you think, in that what happens when if I unplug my machine from this port and plug it into a different port? You could just do that. The switch has to learn that you've moved your machine from one place to another. And it does this learning by essentially watching the packets as they come in. As the packets come in, it said, oh, I haven't seen that address before, that must be someone who's just plugged in. I'll remember that for future use in case someone needs to send a packet to them. So switches do learning of where things are. When we talk about ARP, the address resolution protocol later on, this is part of what switches need to watch and remember. But the point about switches, they reduce the number of possible collisions. They're better than hubs in that you can have multiple conversations going on simultaneously. So in this picture, this host can be talking to that host at the same time as this host talking to that host, because the signals are not colliding. So more things can happen simultaneously. And increase the throughput. Increasing the total aggregate throughput. You've still got the 10 megabits to a given destination, but you can have several 10 megabit conversations simultaneously. So the collisions are reduced, but not entirely eliminated. You could imagine this situation that this host and this host both want to talk to the same destination. And so the switch, a naive switch, would send out both signals at the same time. Well, a switch wouldn't really do that. This would be a collision happening in the switch. The switch would have to realise something was going on and not put a bad signal out. It's not a collision on the shared wire, it's a collision inside the switch now. So there still is sharing going on. It's still a shared medium. The output links are shared. The links to the destination are still shared. So switches have to deal with this. And the way switches deal with this are very interesting, and multiple ways of doing it. And Some of them simply generate a collision signal to tell one of them to stop, or some of them store a packet and then forward it on later. All kinds of clever stuff. But switches are very complicated bits of equipment. Fortunately, you don't have to care, you just plug something in and it works. They have techniques to avoid collisions as much as possible. Again, reducing the number of collisions means more packets go through without problem, faster data rates, which is a good thing. So exercise for yourself, go away and read about store and forward and cut through. A couple of techniques switches might use in order to improve throughputs. And then we consider what needs to be done when the network is extended by daisy chaining switches. The switches can plug into other switches, plug into other switches, can plug into the hosts. So signal goes into this switch, it sort of learns somehow the destination is 3 switches over that way and 3 down there. How does it do that? Well, let's go and find out. So switches pretty much where we are today in terms of this kind of technology. But I suppose the big difference we have today is rather than going at 10 megabits, they go a gigabit or 10 gigabits or whatever you decided to pay for. And you go down PC World, you can buy was it 1 gigabit or what? I can't remember. It's probably a 1 gigabit switch for 20 quid. It's a sort of consumer technology these days. But certainly very fast. And essentially everything else about Ethernet hasn't changed. Speed has got faster and faster and faster, but everything else is more or less, and wait a bit here, but more or less the same as it was back in 1980, whatever. So it's a technology which has grown massively over the years. So let's have a look at what is actually the signal, the content of the signal on the wire. An Ethernet frame. Remember, frame is another word for packet. So an Ethernet frame has got 6 bytes of destination address, followed by 6 bytes of source address, followed by 2 bytes of type, followed by up to 1500 bytes of the actual data we're trying to send, followed by 4 bytes of something called a cyclic redundancy check. This would be sort of as a layer up in the link layer, but this needs to be suitably encoded into electrical signals. And again, won't go into detail, but it's not simply a +1 bot for a 1 and a 0 bot for a 0. It's a lot more complicated than that. Anyway, so destination host address and destination, source address. 6 bytes. So these addresses are 6 bytes long. 6 times 8, 48 bits of address. 2 bytes to indicate what kind of data do we contain. By kind, it will really mean what is the protocol of the next layer in the data field. So you might expect IP packets in this. This is an Ethernet frame containing an IP packet. IP is a hex 0800. So the number 0800 would be in the type field. The type means type of protocol, not type of data, like it's a video or it's a document. It's the protocol. And this type field allows software which is just read in this packet to say, okay, what am I going to do with the stuff in the data field? What am I supposed to do with it? This type field says it's an IP packet, so give it to the IP software. Or it's some other kind of packet, so give it to the local bit of software that deals with the next layer up. This is a link between this layer and the next layer. Tells the receiving host or sending host what you're supposed to do with the data. Otherwise, how do you know what is in the data field? Could be anything. Just tell you what it is. The data up to 1500 bytes. 1500 bytes, number not too big, not too small. Remember all the stuff about packetization for resilience, all this kind of thing. You don't want to be infinitely large, that would be a continuous connection. You want stuff in packets, how big are your packets? Well, it turned out 1500 was the finger in there, it turned out to be the right kind of number for the technology of the time. Back in 1980, mumbly, 1500 bytes was the right kind of size thing. If we redo it with the modern technology, you'd want the packets much bigger, because everything moves so much faster. But 1500 is the number. We've got the data. After data, we've got this header, but we've also got a trailer after the data. It's a cyclic redundancy check. This is one of those little things that were put in there in order to spot corruption or errors in transmission. And the way this works is, at the sending end, you assemble your frame with an address, a type field, and some data, and then you run a little function called the cyclic redundancy check function. It's sort of specified in the documents, go read the documents, but it goes through all the bytes and computes a little 4-byte value from all the bits it reads in the packet, in the frame. And it stuffs the value it finds in the CRC field. Sends off the frame. The other end receives the frame, reads everything, does the same computation at all the fields, and compares what it's just computed against what it's received in the CRC field. If they're different, then something has gone wrong in the transmission of the data. Somebody has come in and mucked around with maybe my data, or maybe an address or something, or maybe the CRC itself. But something has gone wrong. This is evidence of corruption. And Ethernet says, if the CRC doesn't match on receipt, drop it. Do nothing more, just throw away this packet, it's corrupted. If the CRC turns out to be the same, the one you computed turns out to be what you received, it's a good bet that the data was not corrupted. It's not 100% certain because you can't really encode thousands of bytes worth of information into 4 bytes, but it's a good indication that the data was not corrupted. There's a small chance it might be, but mostly it's not. So this is an easy way to check or spot corruption. Not 100% secure, but good enough. So, at this point, we'll look at the addresses, these two address fields inside Ethernet frame. And you've got to have addresses for the frame to know who is this frame for. The frame floating around on the shared medium, who's it supposed to go to? Because it goes to everybody, which is a shared medium. The destination sees the frame and knows it's the frame for it by reading the destination address. So every host sees every frame, so the real problem is, how does a host know a frame is for it? And it's exactly what this value does. The way it works is that every Ethernet card, that is the thing you plug in your network into, has got a unique address built into it. That's under the manufacturer. The manufacturer makes the chip, they burn in a particular number, and then that's the Ethernet address of this Ethernet card. You may be saying, that's not the entire truth, but true enough for now. There are ways of fiddling around this, but just assume for now, every separate Ethernet host has a separate Ethernet address. And so the destination address allows an Ethernet card to spot, oh, this is my packet, this is my packet, this isn't my packet, by simply looking at the destination address. There's a very long-winded way of saying something simple. Look at the address on the destination, is it me or not? If it is, it can read and process this frame. The reason I'm being a bit long-winded here is to sort of indicate that there is actually security issues here that if we had time, we would worry about. In that, what's to stop my Ethernet card reading everybody's packets as they go past? One for me, one for me, one for you, I'll read that anyway. The answer is nothing. The way the Ethernet protocol works is, you can read anybody's packets you can see. And so there's a security issue that if you're that way inclined, you could exploit it. You can definitely read lots of other people's traffic on a network like this. It is very easy. There are just tools to do it that you can pick up and use. So if you want to sniff other people's traffic, it's just sort of trivially enabled. But anyway, let's ignore, like designers of Ethernet, let's ignore security. The destination address is, this is for me, the source address is, who is this from? Packet arrives, I know it's for me by the destination address, I know who to reply to by looking at the source address. This is an address that I would put on as the destination on reply packet. So these are 48-bit values. 48 bits, typically written as hexadecimal, separated by colons. Quite why they chose that as the favourite representation, well, probably some engineer decided hex is more sexy than decimal, so let's use hexadecimal. Anyway, the important thing to realise is that they are not hexadecimal numbers inside them, there are bits, we are just writing them down using hexadecimal. For the convenience of the reader, nothing else. If you looked inside, you just see ones and zeros going past. In fact, there is actually a bit of information. The manufacturer can be deduced by looking at the first few bits of one of these addresses. If you want to find out the manufacturer of the Ethernet card that sent this rain, you can sometimes figure it out. But anyway, 48-bit 6-byte value. We're going to sort of pause and come back to Ethernet addresses shortly. But for now, Ethernet is a nice simple thing where you've got your data, who's it from, who's it to, what is it, and check the errors. Then you've got the CS and ACD on top of it to actually send these frames backwards and forwards. If you're looking carefully, it says data 46 to 1500 bytes. There's actually a minimum number of bytes you can send in a frame, which is rather curious. Suppose I've got 10 bytes to send, what am I going to do? And secondly, why is there a minimum number of bytes? And I will let you go and find out for yourself. That's a sort of mildly interesting question, but there's a minimum as well as a maximum. You can understand why it's a maximum, but why is there a minimum? Anyway, so we've got this idea of a shared medium. And it works well enough when you're on a sort of local network. Everybody's sharing the costs of the hardware. And having a shared medium works well enough when you're only sending to somebody on your local network. You put the packet on the network, there you are, everybody on the local network can see it. So that's sort of nice and easy. But we do have the question of what happens when the destination is not on the local network. After all, most of the time you're watching YouTube videos, and certainly YouTube isn't on your local network. So packets have to get off the local network somehow. So what happens non-locally? You can't do the same thing as your local network and just share everything. You can't imagine the entire internet being a single shared network. Of all the billion hosts on the network, everybody can see everybody else's traffic. That would be a nightmare for many, many reasons. You can't simply broadcast the packet, put the packet on the local network and hope the destination sees it. There'd be so much other rubbish on the network that this wouldn't be a chance. But that even forgets the problem that the destination might not even be an Ethernet anyway. I'm plugged into this electrical thing, you're plugged into a completely different electrical thing with a different frame and different electrical properties. It just doesn't make sense. I can't broadcast to a shared world because every chunk of the world is different in technology. And we probably don't even know what kind of hardware the destination is running on either. You might have a guess that it's working on Ethernet, but maybe it's not. Maybe it's working on optical fibre, maybe it's working on ADSL, maybe it's working on Wi-Fi, maybe it's working on cellular phones, whatever. You don't even know what kind of hardware most of the traffic that you send is travelling over. So this means that the destination might not even have an Ethernet address, because it's not on an Ethernet. So you can't build Ethernet frames and send it out to the world, because the world is not an Ethernet. So what we have to do is have other kinds of addresses, hardware-independent addresses. Ethernet addresses, they're an Ethernet. Other kinds of addresses and other kinds of hardware, they're not Ethernet. We don't know what kinds of hardware you've got. So you've got to have something which is hardware-independent, software addresses. Hardware-independent addresses, sometimes called software addresses, sometimes called network addresses, many names. And this is going to be in the next layer. The next layer is going to be dealing with these other kinds of addresses. So the next layer, as I've mentioned previously, is rather unexpectedly called the Internet Protocol. The next layer in the Internet Protocol is called the Internet Protocol. Its major function is routing. As to say, where do packets need to go next? Packet from here to Australia, which direction do I need to send it? What route does it take? This is going to be the major function of the IP layer, the networking layer. And so we're going to find, amongst a big bunch of other stuff, the IP layer header has got IP addresses in it. These software addresses, machine-independent addresses, are dealt with in this layer. Hardware-independent, as I said, same format across the entire internet. So any machine you want to talk to has an address, and it's in a format that you know. So as long as you can know the address, you can build an IP packet with the right kind of address in it, and then send it off to the hardware layer, and let the hardware layer do its own thing. IP addresses, same format across the entire internet. So this is the format of an IP packet, a network layer packet. At the bottom we've got the data, and here we've got a header on the front. And conventionally, you read this left to right, so this is actually lots of bits strung out left to right, left to right, left to right, all the way down the bottom. You just sort of stack it up like this to fit it on the page. You should really imagine this as a really long and thin kind of thing. So versions, header links, lots of stuff in there. At the moment, we're only going to be really worried about these two fields: address field, source address, destination address. Same kind of idea as in the layer underneath. You've got a source address, you've got a destination address. But now these are software independent addresses. A lot of other stuff, important, but we're not going to talk about it right now. We're going to stick to talking about addresses. These are 32 bits, 4 bytes, 4-byte addresses. And again, for reasons not really clear, but they're typically written out as decimal numbers separated by dots. But you should think of it as a 32-bit thing, 32 bits. Again, this is a convention to help you understand and help you read these addresses. You should read that as a byte whose value might be interpreted as 108, followed by another byte, whose value might be interpreted as 38, followed by another byte, followed by another byte. Don't think these are decimal numbers, these are just ways of representing the bits. For no particularly good reason, Ethernet addresses are written in hex, where IP addresses are written in decimal. Historical accident. But that's the way it is. I rather suspect it's the different kinds of people who use these. IP addresses are normally at the software end of things, where Ethernet addresses are normally in the hardware end of things, so engineers versus computer scientists or something like that. But that's the way it works. But remember, you do this purely so you don't have to write out 48 ones and zeros. Do that if you like. You just spend a lot of ink, but for no great purpose. So, these four byte addresses have structure. Ethernet addresses, essentially, it's a number, you buy another one, it's a completely different number. There's no relationship between Ethernet addresses. IP addresses, there's definitely relationships between the IP addresses of hosts on the same network. If we look at an IP address like 138.32.14, which would be an address of a host on the university's network, it turns out that the first half, 16 bits, the 138.38 part, is actually a network address. That is to say, the network owned and run by the University of Bath. Any machine within the University of Bath will have an address starting 138.38. Yeah, a bit of a hand wave there, but 138.38 says University of Bath. Within the University of Bath, you've got another 16 bits to tell you which machine on the university network. So the 32.14, which is 16 bits, tells us there's actually a particular host residing on this network, the 138.38 network. Here we go. If you feel like writing out ones and zeros, this thing is the address of a host on that thing. So you can do this if you like, but it's much easier to write things out in decimal. But of course, inside the machine, it's all in binary. So we've got networks and hosts on networks. This is the structure. And then this is actually a very important thing to deal with routing. Because it means anywhere else in the rest of the world, able to send a packet to the University of Bath, it starts off 138.38. All the routers in all the networks in the world see 138.38 and they think, aha, I know where that is. It's that network over there in the University of Bath. If IP addresses were allocated at random, each individual address, every host in the entire world would have to know where everybody lives. Each individual address would go to a different place. They were grouping together a big bunch of addresses in one place. So anything that starts 138.38, every router in the world knows where it is. Only when the packet actually reaches the university does any local knowledge have to be used to find out which particular machine in the university are we talking about. Machines outside the university don't even care about the bits after the first 2 bytes. They don't even look at them because they can't do anything with them. When it gets to the university, then within the university, it uses the host part to determine where in the university. And in fact, it turns out that this idea recurses in that the host part actually splits further into a subnet and a sub-host part. So the 32.14 actually splits into a subnet part. It says a subnet within the university, and then the host on that subnet within the university. For exactly the same reasons. University is big and complicated in lots of networks. You just look at the subnet part, which department in the university to send it to, it reaches that department, and only then you actually need to look at the host part to find out which host on that network. So you've got this hierarchy of networks again. This could actually carry on indefinitely, but you see my notes. Subnet addresses to locate within the university, network addresses to locate on the internet. Local routing within the university. Because once your network is big and complicated, you've got a routing problem locally as well. When you've got dozens of networks, how do you know where to send your packets? Remember that picture from a long time ago of multiple routes between different parts of the university. So, a point I want to make at this stage is that split into a network part and host part may not be on a nice neat boundary, might not be down the middle. If you look at address 3101, it actually splits into a 3 for the network and a 101 for the host. There's a lot more complication to go on here, but we won't worry too much about it here. The point to take away is that there is a split somewhere, and it could be essentially anywhere these days. A network part and a host part. Might not even be on a byte boundary, could be halfway through a byte. The reasons for that, well, you go to find me a unit on networking, you'll discover. But anyway, these IP addresses, independent of Ethernet, independent of any kind of hardware. It doesn't really matter whether I'm sending to a destination on an Ethernet or any other kind of network. I use an IP address that identifies that machine. But having solved one problem, that is having a uniform addressing mechanism, regardless of hardware, to solve that, we've introduced another problem. This problem is this: there's 2 addresses now, a hardware address and a software address. How are we going to link the 2? Suppose I want to send data to a machine with this software address, 128.342, on the local network. That's what my application says. Send a packet to this destination. This goes through all the various layers, being presentation, session, or whatever you want to do. Transport gets down to the IP layer. IP layer sticks it in a packet with 128.342 as the destination address. Puts my IP address, the source address, and then hands it over to the next layer, the link layer. The link layer wants to wrap it up in an Ethernet frame. So the link layer can put this on the Ethernet. So it's going to have to fill in the destination address, source address, and the other bits and pieces. You can't send a packet until it's in an Ethernet frame. Was that a pointed cough or just a cough? Within just a second. You can't send a packet until you've got an Ethernet address, because that Ethernet address tells the hardware where to send it. But Ethernet doesn't know about IP addresses, and IP doesn't know about Ethernet addresses. They're totally separate things because of, well, all the reasons I've just talked about. I might have a software address. What is its hardware address? There's no correspondence between these 2 kinds of address. They're totally separate. So they've got to be. That's the design of software addresses. So if we have a pause here, we can come back and discover how to bridge this gap in 10 minutes. Coming into hardware addresses, we need 2 kinds of hardware addresses. One, because they've got different roles, right? One for the software, one for the hardware. And there's a gap between them. You might not know one, like the software address for your destination, but that's not enough. To actually physically send it, you need a physical address, the hardware address. And there is no correspondence at all between these 2 kinds of addresses, because they're intended, software addresses are intended to be completely independent of hardware. So there cannot be any relationship between hardware and software addresses. And then they've got different ways of being allocated. IP addresses are structured around networks. They've got this structure that says this is a network, this is a host on the network. Ethernet addresses are determined by the people who built them, the Ethernet card manufacturers. So that they're really quite different beasts entirely. So we're going to have some kind of address discovery. That is to say, given a software address, I've got this packet I want to send to this IP address, find me a hardware address that corresponds to it. From a software address, find the corresponding hardware address. Address discovery. And this is done by a very simple little protocol called the Address Resolution Protocol, usually just called ARP. It's so simple you barely call it a protocol at all, but it's a very important one because it bridges this gap between the software and the hardware. or if you like, between the network layer and the link layer. It's a protocol that lives in the link layer, which is to say, it's normally associated with the link layer. Essentially, broadcasts a special kind of frame, an ARP frame, on a local network, local medium, and that the broadcast is essentially who has IP address the thing you're looking for, 138.38.32.42. Whatever it is. It's essentially that me stood at the front and saying, anyone here called Alan? And then presumably Alan says, oh, it's me. Anyone called Alan? Only shy people called Alan. Okay. Anyone called John? That'll work. You're a bunch of weirdos, aren't you? Okay. So, oh yeah, that does illustrate what happens when there is no reply. There you go. Okay, so essentially it's a broadcast and somebody replies. The host with that particular software address will reply, say, oh, it's me, and here is my hardware address. This broadcast has to be put in an Ethernet frame. An Ethernet frame has to have a destination address, but this destination address is exactly what you're trying to find. So you just have to fill it in with something. In this instance, you stick in a very special address of all Fs, or ones if you like, which is a special broadcast address, a broadcast Ethernet address. And so this ARP frame would go out with this address on it. And all the hosts on the local shared medium would see this and say, not for me, or Alan would see it and say, aha, this is me. And then send a reply. Frames with these addresses are supposed to be read by every host on the shared medium. Just in case it's a message for them, they should listen to all of these. Normally they'd only specifically listen to the ones with their own hardware addresses, because those are the packets which they should be reading. Occasionally they listen for everybody's Ethernet addresses when they're trying to listen in on other people's traffic. But a broadcast address is intentionally supposed to be read by everybody. These ARP frames are purely a local thing. They never get forwarded off the local network. Off the local network means onto somebody else's network, maybe different hardware. It doesn't even make sense to ask for the hardware address of somebody who's not on your local network. It's purely a link layer protocol. Link, as in the link from you to the next host. So all the hosts on the local network will hear this broadcast, and you hope that the right one will reply. It replies with an ARP response frame, which is essentially a frame going back to the host that asked the question. And essentially, the content is it's me, and here's my Ethernet address. So it's a very simple call and response kind of a program. Like I say, it's very simple. But again, you should note that there is another security issue here, in that what's going to stop somebody else answering an ARP request? So, is there anyone out there called Alan and say, oh, me, send all your data to me. I'm Alan, really, that's true. There's nothing to stop other people answering on behalf of the actual host. And then all your traffic will go to this interloper. So, again, security problem. On the whole, the real world, it doesn't happen a lot, but the potential is there. It's a security issue for people who are already on your local network. If you're already on the local network, you might be able to do something bad, but if you're already on the local network, you've got lots of other bad things you can do anyway. Anyway, security, I highlight these kinds of issues because security is a problem at all levels within the internet. And as I said previously, these protocols weren't really originally designed with any thought about security. They just wanted them to work first. Okay, so the operating system that sent out this ARP request gets a reply, gets the Ethernet address it's looking for, and now it can actually go away and send that original IP packet that it was trying to send in the first place. It's now got the corresponding hardware address for the software address it already knows. It can now build the Ethernet frame, it can now send the Ethernet frame, and that Ethernet frame will go to the right destination. After waiting for the ARP customer reply. So it sounds like whenever I want to send a packet, I have to do all these ARPs to find out where to send it. Another packet, do I have to do another ARP? Another packet, do I have to do another ARP? Well, clearly you don't want to do that too much. Not yet? Yeah. So, there we go. So we don't want to have to do an extra send and reply for every data packet we send. We want to send a data packet, we have to do an ARP first. Not so good, it'd be really, really slow. So what happens is the operating system does it once, the first time, and then remembers the answer. And so the operating system remembers that after having done an ARP, it's got this relationship stored somewhere in the operating system, so it just reuses it. The relationship, or whatever these addresses are. The ARP cache. And depending on the operating system, you can go and look at the current things installed in your ARP cache just to see which machines your host has been talking to recently. These things are just a cache. They're there to remember the recent associations of software and hardware addresses. They're a cache, and they time out after a given amount of time, 20 minutes or whatever the administrative law machine has set. And the reason is that this association is not a permanent forever and ever and ever association. It's the association on this machine with this hardware has this software address right now, but maybe later on that machine has gone away and another machine has come back, come in and using the same software address, but it's a different hardware. Another machine is using the same software address. So it's not a permanent association. So this cache has to be timed out. You throw away this association once in a while, and then if the machine still wants to talk to that, it will do another ARP lookup later on. So it does an ARP maybe once every 20 minutes or whatever. It's not so much. It's a bit of an overhead, but it's not so much of an overhead. It's certainly a lot better than doing an ARP for every package. IP addresses are not tied to the hardware. So this is, by its very nature, is not a permanent association. But it's just there long enough so that it's worthwhile remembering it inside the operating system. As I said, once the cache is expired, the next time you have to communicate with that IP address, the operating system will just do another ARP, just to make sure nothing's changed, or maybe something has changed. So ARP, purely a local network protocol, is there to deal with things on the same bit of hardware as you, the same shared medium as you. The ARP broadcasts never leave the local network. It doesn't make sense, because off the local network might be completely different hardware. Never forwarded. So the rest of the world have no clue about what's going on within a network in terms of hardware addresses. They cannot have an idea of what's going on within the local network about hardware. It doesn't make sense to do so. Hosts outside our local network could be completely different technology. This is sort of one of the strengths of the internet. You can plug together things of completely different technologies. You can plug an optical thing into a Wi-Fi, into an Ethernet, into a whatever, and they all talk to each other. At the hardware level, they're different. The software level, they're the same. The purpose of ARP is local. A local thing, the local hosts. It doesn't even make sense to go non-local. But non-locality, talking to things which aren't local, is an essential thing that you need to do. What happens when I want to send a packet off the local network? Go watch a YouTube, which is stored somewhere in California or something like that. Not on your local network. ARP is a sort of banging on, is a link layer protocol. To deal with things off the local network, we need to go up to the next layer, the internet layer. And then this takes us right back again. We sort of swung into IP briefly and came back. Now we're talking about IP layer again. But there is a link between the non-local case and the local case. Because ARP still has to be involved in the non-local case. Now, the way routing works, well, generally speaking, it's very complicated. But for the end host, that is, me sat at this machine, you on your phone, the end host, it's really quite simple. If a destination that you're sending packets to or is on the local network, on the same network as you, then put it on the local network, job done. That's the good thing about shared medium. Put it there, everyone has it. It's end of story. Slight question of how do you know it's on the local network? Well, remember this network part of the address, host part of the address. If you've got the same network part of your address, then you're on the same network. So again, the structure of the IP address is working for you. It's actually very easy to tell whether the destination is on the same network as you or not. To send the packet to the local host on the local network, you probably do the ARP stuff to get the hardware address to the thing on the local network, and then you send the data. Nice and easy. So this is exactly what I've just been talking about. And you look at the Ethernet frames it goes past, and on that frame you see destination Ethernet address, destination IP address. IP address, destination address, both of the destination. That doesn't sound terribly controversial. Destination hardware address, destination software address are the addresses of the destination. And I'm not just repeating words in a different order. The difference happens when the destination is not on the local network. Local machine says, I want to send a packet. It's on this IP address. Oh, that's not my local IP address, my local IP network address. I'm going to give it to somebody else to solve. The way end hosts route non-local packets is give it to somebody else to deal with. Solution adopted, send the packet to a gateway host and let the gateway host deal with where to send it next. Now, gateway host is just a host on more than one network. It's the gateway off the local network, if you like. So if this host is sending to that host, it just puts it on the network. If this host wants to send to somewhere out there in the big bad world, it says, oh, keep it at the gateway, let the gateway sort out where to send it next. The benefit of that kind of thing is the software in the host is kept simple. Is it local, non-local, is the only question you need to ask. Send it local, give it to the gateway, is the only solution it needs to have. All the complexity is in the gateway, and indeed all the other routers out there. They're going to have to do something complicated, but the millions of end hosts, the billions of end hosts, they don't have to do anything complicated. Keep the complexity localized. But anyway, so the host just sends the packet to the gateway, and the gateway presumably forwards it on to the next hop. But I just said the packet sends it to the gateway. Sorry, the host sends it to the gateway. There's more to that than meets the eye. The packet's going to the gateway. So to send the packet to the gateway, I need to send the packet to the gateway. That is, put it in an Ethernet frame whose destination address is the gateway's hardware address. We need to do an ARP for the hardware address of the gateway, not the gateway, the ARP of the hardware address of the destination, which doesn't make sense because it's not local. We have to say it's going to the gateway next. That's the next bit of hardware we're going to hit, giving me the hardware address of the gateway. Even though the IP address of the ultimate destination is the IP address to somewhere out in the world, the local address is still a local address, that of the gateway. And so when you see the frame go past, frame going whizzing past to the gateway, I look at the frame here, I see it's got an IP address of something out there in the world, but it's got a hardware address of the gateway. In this case, the two addresses are completely unrelated. Local stuff, the addresses are related, and non-local stuff, the addresses are completely unrelated. Because the local address is to do the local thing, the software address is to do the global thing. The physical and network addresses on the Ethernet frame are completely unrelated. So when you look at these frames going past, don't always assume that the two addresses in the network layer and the hardware layer are for the same machine. The hardware address is for the hop, the software address is for the ultimate destination. And this again is another reason why we need two kinds of address, software address and hardware address. Because they're doing different things. One's for a hop and one's for the ultimate destination. They're completely different things. I've been talking about in terms of Ethernet isn't actually restricted to just Ethernet. It actually can link up any pairs of software and hardware address. So in most of the cases you're ever going to see it, it's going to be Ethernet and IP. Maybe Wi-Fi and IP, but not a lot more than that, I suspect. We've got these different kinds of addresses. These different layers are doing different things. This one I'll sort of give a bit of, it's a bit of a hand wave, it's a bit of a generalisation. The layers, network layer, physical, the link layer and these kinds of things, are doing different jobs for us. The link layer and the physical layer is really sort of a point-to-point, getting from this machine to the next machine on the local network. It's a point-to-point thing, single hops in a local network, and it has hardware addresses to find out where to hop to next. The network layer, the IP layer, source host and destination hosts across the internet. So maybe consisting of many hops, but a long distance thing. This is where we have software addresses. And it turns out that when we get to the transport layer, we won't really have time in this unit to talk about the transport layer, there's actually another kind of address going on that tells us client process to server process. The process on this machine to the process on that machine. The program running on this machine to the program running on that machine. And this is what port numbers will do for us later on. As I say, we won't really have time to talk about that. But with different layers, they've got different different jobs in terms of connectivity. Local, global, and then within the machines. So again, this is why we have multiple layers. They're doing different jobs. So comparing hardware and software addresses, hardware addresses are hardware dependent, surprisingly. Essentially distributed at random. There's no relationship between two hardware addresses on the same network. They're there for local routing. Software addresses are hardware independent, have structure, network part, host part, and have structure in there to deal with non-local routing. So they're really very different kinds of things. And this is why we need to have ARP to join one to the other. Different hosts can have the same software address at different times. The software addresses are, here's an address, use it, machine goes away, another machine comes in, it might get the same software address. The same host can have different software addresses at different times. Me in the coffee bar, my machine's got a particular software address. I walk to the library, my machine might get a different software address. Its hardware stays the same, but the software address differs. So again, they're doing different things, and hardware is constant, but software changes in terms of addresses. So Something to think about for yourself. What if it wasn't structured like this? What if every machine had a fixed address? What kinds of security or privacy issues might there arise if a given machine always had the same fixed software address? Just think about the kind of things that might be possible if this happened. So again, this is yet another reason why a good separation between these two kinds of addresses is important. Have a think yourself. Okay, so next problem. I've been talking about IP addresses. I've been saying, oh, just send it to this IP address. How did the machine get an IP address? Hardware addresses are the problem because they've built in the chip, like the Ethernet chip at the time of manufacture. Software addresses get assigned to machines. How does this work? How did you turn on your laptop? It's got an IP address. Where did that appear from? The simplest way, the original way, was there's a file somewhere inside the machine which has got an IP address, and the machine uses that IP address. Configuration file somewhere. And certainly in the early days of the internet, this is how it was done. Machine booted, it read a certain file, found an IP address, and just used it. Then that file had to be written by somebody, an administrator, and the administrator had to make sure it was a good, decent, relevant IP address. Network parts, sub-network parts, unused, you can't have duplication between IP addresses on the same network and all these kinds of things. It's got to be a unique network that fits into the network, the current network. It's not non-trivial to assign addresses to machines. Originally, somebody had to do that, and they would have a big list of, in their office, probably on the wall, this machine has this address, this machine has this address. It's not always feasible to have somebody administer a machine every time it needs a new IP address. Not all machines have administrators. You go into a random house, most people in that house wouldn't have a clue about what the internet is in the first place, let alone what an IP address is. They won't be able to administer machines. Some people simply aren't competent enough to understand the rules that you need to follow to pick the correct IP address. Some installations have too many machines. You might have an administrator, but there's just too many machines for them to code. So think about all the PCs in the library. Don't know how many hundreds are there in the library. But imagine if somebody had to go in there, sit down at machines, configure it. Sit in the next machine, configure it. Sit in the next machine, configure it. It wouldn't be a decent way of spending your life. And that's only for the fixed machines. What about machines that are coming and going all the time? Some installations have machines that come and go. So you walk into the library with your laptop, it gets an IP address from somewhere. You didn't have to go and knock on somebody's door and say, please can you configure my laptop? There was a magic pixie somewhere that gave you an IP address. That can be the only solution. Really, it wouldn't be cost effective to have some person or people sat there administering all the machines that come in, or no email, I'm going home. So you've got a fairly simple, well-defined, but time-consuming task. Now, what do we know is good at doing these kinds of things? Computers. Administering IP addresses is best done by computers. And so there's a protocol, the Dynamic Host Configuration Protocol, DHCP, which is there to do this for us. Dynamic Host Configuration. It's there to configure IP, well, amongst other things, IP addresses. It's a protocol that your machine understands and can ask the network to say, give me an IP address. When a machine needs an IP address, it uses this protocol to get it. So, host loops, or you're familiar with your laptop or whatever, newly connected to a network. It needs an IP address for that network. So it's on that network. It makes a DHCP broadcast. So again, it's a bit like it stands there and shouts, anyone can give me an IP address, please. A broadcast goes to all machines on the local network. It sounds superficially similar to ARP, and it does a broadcast, expects a response, but there are quite significant differences here. It can't do anything apart from ask everybody, because it doesn't know the IP addresses of any particular host. I don't know his name, I don't know his name, I don't know his name, so I can't ask him anything directly without knowing his name. So I just have to say, anyone out there can do this for me. In contrast with ARP, where ARP is there to find a single hardware address for a single host, DHCP, you tend to have one or two machines, quite often just one, maybe two for resiliency or crashing and all this kind of stuff. A machine called DHCP servers. That is machines running, listening for running the DHCP protocol, listening to DHCP requests. Most machines won't be listening for DHCP, but maybe one machine on the network has been configured to do this. One machine has been configured, well, that means that somebody out there had to configure it, but at least it's just one machine and not hundreds of machines. In contrast with ARP, this is an IP level broadcast, not a hardware level broadcast. It's got to send a packet with an IP address on it, and it uses a broadcast address, or ones again. Quite often a broadcast address is just addressed with all 1 bits. But notice this is a different address than the Ethernet broadcast address, which is 48 bits long. This is 32 bits long. It's an IP layer broadcast, which is to say it goes to all the machines on the local network, but the word local here might mean something different to the physically local network. Everybody on the same IP network as me, not the same physical network as me. It is possible that a network might comprise physically more than one physical part, but still be part of the same IP network. Again, different layers. So a packet being broadcast to this address might go to more machines than an Ethernet broadcast. Anyway, so this DHCP server, whose purpose in life is to sit there listening to DHCP requests. A DHCP server, that phrase means a program running on some machine. We tend to name the machine as a server, but it might be doing other stuff as well. For our purposes, it's a machine running a program which is listening for DHCP requests. It's one of these bits of lazy language. A DHCP server might be a mail server as well. It might be a web server as well, but we're thinking that there's something specifically serving DHCP. Here's this request. Somebody wants an IP address, looks in its list of free addresses, says, here's one, and gives a reply, a DHCP reply, back to the requesting host and say, here you are, use this address. So again, like ARP, it's a broadcast and reply, but it's unlike ARP, it's a single host listening and replying. So the original host will get this reply, read this packet, it gets us the reply. There's lots of stuff I'm not talking about here. There's lots of really nasty complications that I'm not talking about here. This is the big picture. Gets the reply, reads the packet, inside the packet will be the IP address that's just been allocated, and then it configures itself to use that IP address. And again, so the client, again, what I really mean is the DHCP client program running on that machine. So when this machine turns on, a particular program on this machine starts running, and that program sends a request, gets a reply, and then that program configures this machine to have this IP address. So the big picture is nice and simple, but there are loads of complications. The simplest complication, and there are several others which I can't talk about, but you get an IP address and you can use it. What happens when you go away, when that machine switches off, or you close your lid on the laptop, or you take the laptop out of the coffee shop? When a host is done, it's supposed to inform the DHCP server that it's finished using that IP address. Can I have an IP address? Here you are, I used it for a while. It's supposed to be nice and neat and tidy and say, I've finished, and give that IP address back. This allows the server to say, okay, nobody is now using its IP address, and can reuse it for somebody else. It can recycle the IP address for somebody new. All the free addresses, it's now got a raw free address. However, this nice and neat tidying up isn't often done. Not very many client hosts are this obliging. Quite a lot simply just don't say, I've finished, here, have it back. You just shut the lid on your laptop, it doesn't have a chance to say, I've finished. If the host crashes, it doesn't have a chance to say, I've finished. And if you think about it, if you keep dishing out IP addresses and never getting any back, eventually you're going to run out of IP addresses. Maybe you've got a few hundred to play with. Here's one, here's one, here's one, here's one. Eventually you're going to run out. So there's got to be some way of clawing back these IP addresses which are now no longer being used. The proper way of doing it is getting it back by being told that it's back. But that part of the protocol isn't often followed properly. Sometimes for good reasons. If it crashes, well, tough. So the way DHCP works this is it gives each allocated address a lease time as a period of time. Period of time that the host can use this address. So now the protocol is, can anyone give me an IP address? Here, you can have this IP address for 10 minutes. Okay, I configure myself, I can use it. If the lease expires while I'm still using it, I can send another renewal request and say, it simply says, I'm still using it, can I keep it? Presumably before 10 minutes. Maybe 5 minutes in, you say, oh, I'm still using it, can I keep it for a bit longer? Carry on. Can I use it a bit longer? Carry on. So another part of the DHCP is a renewal request. Can I keep using this? And almost always the answer is going to be yes. It's very rare that you won't get a no back. Can't think of a good reason why you might get a no back. Unless someone else more important than you is trying to get an IP address, I suppose. But well, it's called renegotiating, renewing the lease. And you get it for another 10 minutes. Then maybe 5 minutes later you say, oh, I want to keep it, and get it for another 10 minutes and so on. And the point about this is that if I don't say, can I keep using it, because I've gone away or I've crashed, eventually the server doesn't get a renewal request and says, okay, the lease has expired, I'm having that IP address back. So it's using the fact that there was no renewal request to say the address is no longer being used. So lack of a request turns into a here's the address back. So at this point, maybe after 10 minutes or whatever, maybe it gives it a few minutes longer just to be sure, it says address is now dead, we can use it again. These times, I've been saying 10 minutes or 5 minutes, whatever, you can tune these lease times to whatever you think suitable for your installation. So, for example, you've got a situation where clients are coming and going rapidly. So people come into the library, spending 5 minutes and going away. You look at sort of IP addresses that are being used for about 5 minutes. So you set your DHCP server up to at least times or 10 minutes, 15 minutes or something like that. This means that once someone's gone away, that address won't be dead very long, it'll get called back fairly soon. Longer leases up to infinity, like here it is and keep it forever, can be used for hosts where they're more stable. So this machine here is not going to go away anytime in the near future. So it's probably been configured, the server's been configured to give it an infinite lease, or maybe a week-long lease, or 10-day lease, or whatever. Something that was really, really long. Because we know this host isn't going to go away soon, so why have the bother of asking again and again and again, can I keep it, can I keep it, can I keep it? Because it's still going to be there. So you have an administrator who sets up the DHCP server to tune it for the right kind of circumstances. Long leases avoid the overhead of repeatedly using DHCP, whereas short leases get addresses back quickly once they've gone, once they're no longer being used. Exercise for you to go away and find out the lease times of various places. You use your laptop or maybe your mobile phone all over the place on campus, static PCs in the library, machines at home, machines in coffee shops in town. They'll all get their addresses through DHCP. They'll have lease times. What are they? Are they minutes? Are they hours? Are they days? Find out. And indeed, find the tools to find out. I suspect coffee shops downtown are short leases to encourage you to get out and go somewhere else. But anyway, so these lease times are there tuned for appropriate circumstance. In fact, you'll find your access point on your Wi-Fi thing at home may well be so it looks at the ceiling again. We did find an access point in here once, didn't we? Can't see one now. Anyway, a home access point will probably have a DHCP server in there, and that's where you get your IP address on your laptop at home. Are laptops old-fashioned now? You seem to have lots of them, but maybe they're old-fashioned. It's all thumbs. Anyway, so the DHCP, its main original task was to give you IP addresses. It turns out that it does one or two other useful things as well. Gateways. I mentioned gateways as a way of getting off the local network. How do you know the IP address of a gateway? You go into a coffee shop, you'll be on the local network, you want to go off the local network, the packets have got to go through a gateway. What is the IP address of the gateway of the coffee shop? Well, DHCP will actually be the thing that tells us. DHCP can tell you the IP address of the gateway host, so it knows how to route off the local network. The DHCP server might also give you addresses of name servers. Now we're going to go into name serving in a great deal more detail very shortly, but you're used to machines having names like linux.bath.adc.uk. But IP uses numbers from 3838 to 340. We've got another one of these gaps between a name and a number. How are we going to translate from a name to a number? Well, we're going to ask for one of these name servers. How do we do that? Well, that's to come probably next time, but there's been some machines out there to do this translation between names and numbers. Where are these machines? Where DHCP will tell us where these machines are. DHCP tells us lease times. How long does this address allocation good for? Sometimes DHCP will tell you information like print servers. I'm here, I want you to print stuff. If I say print, which machine should that go to? what the machine the printer attached to, DHCP can tell the print server. I will send email, DHCP might tell you the IP address of a machine that sends email, and so on and so forth. But quite a lot of other things, most of which are never used. Oh, somebody's trying to spam me. Yeah. Suspected spam caller, it says. Anyway, so not many of these things. I guess let them Not many of these are things that are usually sent by DHCP. Almost universally, a DHCP server is set up to give you an IP address, a gateway address, and name server addresses, and release time. All this other trickery isn't used at all, almost always. The potential is there, but you go into the coffee shop, you'll get the basic information to connect your machine to the internet, but nothing more. And again, exercise, find out what kinds of information these various DHCP servers give you. What kinds of information do you actually get? And I rather suspect it will be just those things. Okay. At DHCP, there's much more we could talk about it. Multiple DHCP servers and all this kind of stuff. The actual protocol is more complicated than this, but we've got the basics. I do want to talk a bit about IP addresses. These are 4-byte addresses. The big problem is there aren't enough. The internet has grown beyond all expectation. More and more addresses are needed all the time. And every host that you want to talk to, you've got to have an IP address. One of these 4-byte things. It's got to have a unique 4-byte address. It's got to be unique, otherwise you don't know which one you're talking to. Unfortunately, there aren't any unused addresses out there. All addresses have been allocated. And you might think 32 bits of address, that sounds like a lot, and it gives us 4 and a bit billion different destination addresses we can talk to. When they first devised the Internet Protocol, they thought 4 billion, that's a huge number, isn't it? 32 bits is enough. There's probably more than that telephones out there. And then you think about all the other machines connected to the internet. Simply, 4 billion is not enough addresses to talk to run the internet. So there's clearly something going on here. One of the many things being done is to increase the number of addresses available. And the way they're doing it is by having a different version of the IP layer protocol. The current IP layer protocol is version 4, IP version 4. Bit of history, going to learn about what happened to version 1, 2 and 3. Slowly being introduced is IP version 6. Again, a bit of history, what happened to 5? You'll find out. But the idea is you pull out layer 4, you pull out IP version 4, you plug in IP version 6, stuff above works the same, stuff below works the same, and so you've got a working internet that's got many more addresses. The key feature, we're talking about addresses right now, is that it's got 128-bit addresses, 16 bytes of address. So, sounds brilliant, lots more addresses. Until you sort of read about, again, the history of these things. Devised in 1996. About 20, lots of years ago, decades ago, last century. How come it's not being everywhere in the internet? They thought it was needed in 1996, and then we managed to hang on until now, still using IP version 4, principally. So there are issues, but the point is, by layering, you can pull out an old layer, put in a new layer. Well, it would have been that if they'd done it right in their design of the internet protocol. Designers of TCP and this kind of stuff made all kinds of interesting, I'm not sure error is the right word, but features included in some of these protocols actually go across layers. This is bad design. It is simply bad computer science. But at the time, they weren't really thinking about these kinds of things. They wanted something that worked. They got something that worked. It was cast in stone. We've been having to use it for the last 40 years or 50 years, or however long it is. And also, people writing software hadn't made assumptions that addresses are 4 bytes long. Because you look at IP, they have 4 byte addresses. Therefore, every address in every protocol in the world has 4 byte addresses. Again, it's bad assumptions in software. So there's lots of problems in introducing this new layer, which should have been just a push it in overnight kind of stuff. Didn't turn out to be like that. Anyway, the important point, with IP version 6, 128 bit addresses, enough to give every molecule on the surface of Earth its own address. 2 to the 128 is a big number. And you really could literally number every molecule on the surface of Earth with its own IP address. Not going to run out in the near future, as long as we're not too stupid in using them. Addresses are written in hexadecimal again. In why hexadecimal? Well, it's just a bit shorter than decimal. Addresses are written like this. So this is 1, 2, 3, 4, 5, 6, 7, 8 chunks of 2 byte chunks, 16 bytes. And they allow you to abbreviate longer strings of zeros by a double colon. So this would be one of these new addresses. Certainly doesn't fit in the 4 bytes, but you don't want to be writing these things out. And just to give you a feel for the scale of these things, the University of Bath has been allocated a bunch of addresses. They've been given a network that's about that. We've been given 2 to the 80 addresses to play with, which is 281 trillion times the size of the whole internet for the University of Bath alone. And every other university and every other place in the world, that kind of stuff. You can have trillions of internets worth of addresses. You're not going to buy the machines, but you'd have lots of addresses for all the machines. That would be a good place to stop.